Welcome to Apache Spark Performance Optimization on Databricks course series. And in this course particularly, we will be looking at storage aspects of performance optimization or performance tuning. So before we move ahead, let's have a glimpse of what kind of performance optimization we are trying to achieve in this course. Here you can see we have managed to reduce the time from 16 minutes to 2.3 minutes of our query. So this is a performance jump of approximately 6x, that is 600%. Here also from 41 seconds to 6 seconds. This is also a performance jump of approximately 600% or 6x. Now let's understand few points about the course. Who can take this course? So this course is suitable for everyone who is a Spark developer or Spark architect or data engineer who are working with Spark applications to handle big data processing. But you should already know Spark. This is not a course to teach you how to code in Spark. You should already know Spark and Spark internals, the concepts of jobs and clusters and job execution process, all those things. So this course is basically building on that fundamental knowledge and taking you to the next level of Spark performance improvement and bottleneck resolutions. Next, what is the approach? So this course is basically fully case study based or real world scenario based. So we will present a case study or real world scenario and then we will drill down to the main problem. So this course is basically full of hands-on scenario based examples. Next, benefits of the course. So as I mentioned, this course is based on case studies. We will identify the problems of the case study. We will try to understand what is the problem, and then we will try to find out what are the bottlenecks, what are the improvement scope of our application or of the case study that we are dealing with. Once we identify the problem, what is the main root cause of the problem? So we will analyze that. Then we will tune different sets of parameters to mitigate the root cause of the problem, and we will also select best combination of the parameters for optimal results. And once you learn and fully understand all these concepts, you will set yourself apart from the rest of the crowd, both in case of job interviews of mid or senior level architects or data engineers, but also in your organization as well. Once you apply this knowledge in your Spark code or in your Spark application, your code will be running like a magic. That will make you set yourself apart from the rest of the crowd. Let's now have a look at some prerequisites of this course. First of all, you should know Spark programming. So as I mentioned, this course is not for teaching you how to code in Spark. You should be familiar with Spark programming, either Scala or PySpark. Next, you should be familiar with Spark internals and architectures. That means the clusters, drivers, executors, jobs, stages, tasks, how the job execution happens, all these things you should be familiar with. And the next one is you should be familiar with Databricks cloud platform as well, because we will be running the experiments on Databricks. One important note about this course is that the datasets that we are using in this course are huge. Minimum is 10-12 GB and on an average it is 50-60 GB of data. So this kind of huge volume of data, it is not possible to share the data. So the datasets used in this course will not be shared. However, the codes that we will be using in this course will be shared and available to you. Before we wrap up this introductory lesson, let's have a brief introduction about myself. I am Seahawk. I have an ETL experience of 11 plus years, out of which Azure experience is 8 plus years. I am a Microsoft certified Azure data engineer. I have worked various clients across US, Europe and Southeast Asia region. That's all about myself. Grab a cup of coffee and let's enjoy the course. Happy learning. Welcome back. So in this lesson, we will understand what is performance tuning or what do we want to achieve in performance tuning. So we might want to improve the speed of our query or our application or our data pipeline. So this is one sense of performance tuning. Okay. Now there are a couple of ways to measure the speed. First of one is response time. So we may measure the response time of our job, but response time may vary depending on input data volume. So it is not a reliable indicator or reliable metrics. So the better way to measure the improvements of speed is to measure throughput of our job, which represents number of records processed per second or per minute. Okay, so this is a better way to measure the improvement of speed of our job or data pipeline. The second way is to reduce the cost of our resources. Let's say yesterday your job was processing 100 GB of data with 20 core cluster and 80% CPU utilization. Now after some performance tuning, today it is processing same 100 GB of data with 20 core cluster and 60% CPU utilization. So we have managed to save this 20% delta, right, in CPU utilization. So we might use this much of CPU power to another job, or we might take a smaller VM or smaller core cluster and reduce the running cost of our data pipeline or job or application. Okay. So this is another way to measure performance tuning or performance optimization. The third way is to improve operations. Let's say previously your job was failing 5 times of every 100 run due to some out of memory exception or some other bottlenecks. Now after some performance tuning, it is now failing only once or twice every 100 runs. So reduction of job failures leads to improvement of operations, which is another way to measure the performance tuning or performance optimization of our job or application or data pipeline. Okay. Next, let's understand some of the challenges of this performance tuning operations. Okay. So the first challenge is how to identify opportunities. Let's say in your application you have 100 lines of code and it is running fine without any error every day. So how do you identify, or how do you be sure that yes, there is some scope of improvement or some opportunities are there within this application or within this pipeline? So identifying this opportunity is first challenge. So once you have identified that there is some scope of improvement in your job or application, how do you pinpoint that yes, these 5 lines might have some performance improvement scope? So pinpointing this narrow piece of code or identifying the code that is producing the actual bottleneck is the next challenge. Okay. So once you have identified or pinpointed the problematic area of the code or query, the next challenge is how to benchmark. Benchmarking means running the problematic code or query before the optimization and after the optimization, and measuring some key matrices from both the runs. Okay. So a good benchmarking process should have some key features. First of all, it should be measurable. We should be able to measure the key matrices like throughput or CPU utilization or memory utilization for both the runs, that is before the optimization and after the optimization. Okay, so we should be able to measure these KPIs or matrices so that we can compare both the runs. Next is the benchmarking process should be repeatable. So generally what we do, we run the usual version of the code multiple times before the optimization, let's say 2-3 times, and after doing some optimization or performance tuning, we run the optimized piece of code multiple times, let's say 2-3 times. We should be able to run the piece of code with same baseline state or same baseline environment, you can say. So our code should be repeatable. The benchmarking process should be repeatable. The third aspect is it should be consistent. So our benchmarking code should produce similar results both for the previous version and the optimized version of the code. That means every time we run the piece of code, it should produce similar matrices. Okay, so that we can quantify the performance improvement of our optimized version of the code from the baseline version. Okay, so the benchmarking process should be measurable, it should be repeatable, and it should be consistent. The next challenge is distractions. So once we have ensured that our benchmarking process or benchmarking code setup is good, so there might be some distractors as well. So we should look out for these distractors and we should eliminate them in order to get a fair picture of the performance improvement, in order to quantify the performance improvement that we have achieved. So we will discuss all these aspects of benchmarking process in our upcoming lessons. So that's all for this lecture. Thank you. Welcome back. So in this lesson, we'll understand what is benchmarking. So benchmarking is nothing but to run two versions of same code in a controlled environment and comparing the results or matrices that is generated during the run. Okay. So what are these two different versions of the same code? So the first version is the version that is currently running in your application or in your job, in which you think there is an optimization scope or there is an improvement scope. So that is the first version. And the second version is the optimized version of the first code after you have applied the performance tuning idea or performance tuning technique. So we will run these two versions of code in a controlled environment or controlled manner, and we will then compare the results or matrices that is generated during both of these run. Okay, that is basically benchmarking. So what is a good benchmarking? So there are a few characteristics of good benchmarking. First one is it should be measurable. So your benchmarking should be measurable. So when you run a piece of code or a job, let's say, it generates different matrices, right? What kind of metrics we are talking about here? We are talking about the response time or job completion time. Okay, we are talking about what is the throughput of the job, how much memory it is utilizing during the run, how much CPU power it is utilizing during the run, or is there any errors that is generated during the run, like out of memory exceptions. So these kind of matrices we will try to gather, and we will measure our runs based on these different matrices. Okay, now it should be repeatable. So normally what we do, before optimization technique is applied, we run the code multiple times, maybe twice, thrice, and after the optimization technique is applied, we run the code again twice or thrice. Now all these runs should be repeatable in fashion. That means we should be able to run our code from the same baseline state or same initial state in order to compare both the runs in an unbiased fashion or unbiased way. So our runs should be repeatable. Okay. Third one is consistent. So our runs should be consistent as well. So let's say I am processing 100 GB of data, and for the first run it is taking 10 minutes, for the second run it is taking 15 minutes, for the third run it is taking 18 minutes. So response time or job throughput is not consistent, right, between these runs. So which run should I take as a baseline? Because I have to compare it with the optimized version, right? Which of these three runs should I take as a baseline? If my runs are inconsistent, it may produce some ambiguous results, or we might not be able to quantify the performance improvement that we have achieved in our optimized version of code, right? So ideally our runs should produce consistent results or consistent matrices, right? So a good benchmarking should be measurable. That means we should be able to quantify or measure the runs based on different matrices. It should be repeatable. That means every run should be done from the same baseline state. And third is consistent. That means every run should produce similar results or similar matrices. Okay. Next is benchmarking variables. So let's see what are the different variables that we need to fix before doing a benchmark. First one is cluster resources. So we know that cluster size or cluster resources is like compute power, right? So if we have a bigger cluster, our job will finish faster. If we have a smaller cluster, our job will take little longer time. So we need to fix the cluster resources from the beginning so that both the runs, that is before optimization and after optimization, is using the same cluster resources, so that we can compare the matrices in a fair way or in an unbiased way. The second benchmarking variable is data volume. So we need to fix the data volume before we do our benchmarking experiment. Okay, so in both the cases, that means before optimization and after optimization, in both the cases the data volume should be fixed. If we are not using same volume of data, the different metrics that we will be comparing can produce inconsistent results, or we will not be able to quantify the performance jump after the benchmarking process, right? So these are the two variables that we need to fix before the benchmarking. First one is cluster resources and second is data volume. Next is how to benchmark. So let's say your application have hundreds of lines of code. So should we benchmark the full application, the full 100 lines of code, or is it better to first drill down to a particular section of the code and then extract that piece of code and do the benchmarking process for only those lines of code. So it is always better first to drill down to a particular section of the code and then do the benchmarking that portion of the code or that snippet of the code. So we will be first drilling down to that portion where there is improvement scope, and then we'll extract that code, and then we'll be creating a separate notebook, benchmarking notebook, in which we will be running only that piece of code. So this is the procedure in which we will be doing the benchmarking. We will be first drilling down to the particular section of the code and then we will extract it and we will do the benchmarking only for those particular portion of the code. As you may know, Spark transformations are lazy operations. In order to trigger a job, it needs an action, and after the job is done, we will be getting the matrices, right? So every benchmarking should be executed with an action. Now there are some distractors that may produce inconsistencies of results or matrices in our benchmarking process. Okay, so let's see what are those distractors. First one is caching. So caching is nothing but storing data into Spark's own memory or RAM, right? So if we are caching a data or a partition of the data into Spark's memory, it will run faster because in-memory operations are always running faster. So caching can produce inconsistencies or it can produce misleading matrices. So we will be disabling caching before doing the benchmark. Okay, so this is the first distractor. The second distractor is schema inference. So as you may know that Spark gives us the option to infer the schema of a file, right? And in that case, Spark goes to the file location or storage location and it reads certain amount of data to understand the schema of the file. What are the column names? What are the different data types of the file? Okay, so all this information it tries to infer based on the reading of a sample portion of the file. So this is an unnecessary task, and we will be providing the schema beforehand externally to Spark so that it doesn't go and read the data to infer the schema, because it is an unnecessary task and it may lead to inconsistent results that we will be observing and comparing, right? So in order to produce consistent results and avoid these distractions, we will be providing the schema beforehand. Okay, now what is the benchmarking action that we will be using for our benchmarking process or for our benchmarking experiment? So we will be doing loop write. Loop write is specially designed for benchmarking purposes or for performance tuning purposes. The full form of loop write is no operations write. So it is a simulation of a write. Spark will not go and write the data into storage, but it will simulate the write in order to produce the matrices. So it is very helpful in case of benchmarking process or in case of benchmarking experiments, because it is the most consistent action, and Spark has specifically designed loop write for benchmarking purposes. That is why we will be using loop write for our benchmarking action. So this is all for this lecture. So see you in the next one. Thank you. Welcome back. So in this lesson, we'll understand about Spark's architecture. So Spark cluster is nothing but a set of machines or compute resources that are working together to execute a job in a distributed fashion. Every Spark application applies a master and slave architecture and runs independently on the cluster. Master-slave architecture means there is one driver and multiple workers or executors are working under it. All of these executors and driver are individual JVMs running on different machines on the cluster. This means that the driver is running on one machine and the executors are running on different machines. And all of this is managed by cluster manager. Now let's understand how a job execution happens in Spark. When a user submits the Spark application, the driver receives the application code and the input data. The driver then interacts with the cluster manager to obtain resources. Once the driver receives the cluster resources, it then divides the work into tasks and assign them to executors. The executors execute these tasks parallelly on their respective cores. The executor reports the progress of these tasks and the results to the driver, and the driver collects the results from the executor and produces the final output. So this is the flow of job execution in Spark. Once this is clear to you, let's move ahead to understand each and every component of this architecture a little bit more. The first one is the driver. So as you guessed it, driver is the central component responsible for coordinating the execution of Spark jobs. It manages task scheduling, assigns them to executors, and monitors their progress. Next is executors. Executors are worker nodes that execute tasks assigned to them by the driver. They receive data partitions and the assigned task, and then they perform the task on the assigned data partitions. So next, let's understand what are tasks. The driver breaks the application code into small logical blocks, also known as tasks. Tasks are the smallest unit of work in Spark. They are assigned to the executors and run on individual cores or slots. Now let's understand data partitioning. Input data is partitioned and distributed across storage partitions within the cluster. These partitions are then assigned to executor cores or slots for processing. This processing of individual data partition is also known as task, as we have understood earlier, right? And lastly, there is cluster manager. So it manages resources like memory and CPU across the cluster and allocates them to different Spark applications. So these are the different components of Spark architecture. In the next lecture, we will understand the job execution process, that is jobs, stages, tasks, with an example in a more detailed way. So see you there. Welcome back. So in this lesson, we will have a high level understanding about Spark's execution plan. Any Spark application is a sequence of Spark jobs. Each action defines a code block and hence a job. So Spark jobs are defined by actions. The Spark driver will create a logical query plan for each Spark job. Once the plan is done, the driver will break the plan after each wide dependency transformation into stages. Each stage can have one or more narrow transformations, but only one wide transformation at the very end. Spark cannot run stages in parallel. It must run stage 0 first, then stage 1 and so on. That means in a sequential fashion. Now within each stage, there can be multiple threads that can run in parallel. These are called tasks. These tasks are the smallest unit of work in a Spark job. Spark drivers assign these tasks to executors to perform. Number of tasks in a particular stage will be equal to the number of data partitions in that stage. Executors need the code and the data frame partitions to perform these tasks. However, at the end of stage, since we have a wide transformation, output data from different tasks are collected together back to the stage level. The actions require this task output or the information of completed tasks or works to be sent to the driver, and then the job execution completes. So in this slide, the main takeaway is the Spark application is broken down into jobs which are defined by the actions. Each and every job is further divided into multiple stages based on wide transformations, and each stage can have multiple tasks or threads that can run in parallel. Okay, and these tasks are the smallest unit of work in the Spark job. So once these tasks are completed, this information or output will be communicated to the stage level, and once the stages of a particular job is completed, the stage details or the output of the stages has to be informed to the job level, and then the job execution ends. So this is a high level overview of Spark execution plan. Now let's understand this with a sample job execution. Okay, let's go through the sample code line by line. So in the first line, so we are reading a CSV file from my input location and we are storing it in a data frame. Okay. So as you know, spark.read is a action. Okay. Next, so we are repartitioning the data frame into two partitions. Repartition is a wide dependency transformation. In the next line, we are applying a filter and then a select. So both select and filter is narrow transformation. In the next step, we are doing an order by. Order by is also an wide dependency transformation. And finally, we are doing a write, and write is an action. So in the previous slide, we have seen that once we submit this code to Spark, Spark driver will compile this code and it will break the code into different jobs based on actions, right? So in this code, we have two actions. One is spark.read, and after that we have write. So these two are actions here. That is why Spark driver will break the code into two chunks or two blocks. The first one is job 0, which includes only one statement, that is spark.read, because it is an action. And the next one will be the subsequent steps. That means this repartition, filter, order by, and write. Because after this spark.read, the next action is this write operation. So after this job 0, whatever operations we are doing, that will be included into job 1. Okay, the next job. So Spark will divide this code into two jobs because we have two actions. Now for this demo, let's concentrate on job 1. Okay, because job 0 is a single operation, so let's leave it aside. Let's focus on job 1. So once this job is compiled, Spark will do a logical query plan. So let's see how a logical query plan looks like. So this is a basic structure of logical query plan. In the first step, we have the data in data frame that we have read in the earlier job, right? That means job 0. So in job 1, we have the data in data frame. Then we are applying a repartition, and next we are applying a filter, then select, then order by, and then we are writing the data frame to our storage location. So this is the logical query plan of job 1. Now once this logical query plan is created, Spark will try to break this logical query plan into different stages based on wide dependency transformation. The Spark will check what are the wide dependency transformations in this logical query plan. We have two wide dependency transformations here. First of one is this repartition. It is a wide dependency transformation, and then this order by. So these two are wide dependency transformations. So Spark will try to break this logical query plan into stages. So all the code up to this repartition will be a stage. Let's call it stage 1. All the codes till this order by will be another stage. Let's call it stage 2. And the rest of the code will be stage 3. So based on this wide dependency transformation, because we have repartition and order by as wide dependency transformations, Spark will break the job into different stages. Now questions may arise in your mind that why Spark need to break the job into stages based on wide dependency transformations. So to understand that, let's revisit the concept of narrow transformations and wide transformations briefly. Narrow transformations are those transformations that can be applied independently onto each data partition. That means narrow transformation output depends only on single input data partition. Okay. Whereas in contrast, in case of wide dependency transformation, the output depends on data from other partitions as well. So we cannot independently apply wide dependency transformation on a single data partition. So we need to have data from other partitions as well. Once this difference between narrow transformation and wide transformation is clear to you, let's move ahead and let's understand why Spark need to break the code into stages based on wide transformations. Let's concentrate on this left figure first. So at the initial step, we have our input data as data frame. So let's assume that our job doesn't have any wide transformation. So it is a series of only narrow transformations. So in that case, what happens? Spark will apply narrow transformations in this sequential manner, right? And let's say we have 1, 2, 3 narrow transformations and then an action. Okay. Now for easy illustration purpose, we have shown here only single data partition. But in practical, when Spark reads a big file, it reads the file into different chunks or blocks, which are known as data partitions, right? So let's assume that our code has generated 4 data partitions, 1, 2, 3 and 4. Okay. Now as our job only has narrow transformations, so we can apply these narrow transformations individually for each data partition independently, right? Because narrow transformation output doesn't depend on other partition data, right? We have just learned that. So we can run this code for each data partition independently in parallel. So in that case, our job will have 4 tasks or 4 parallel threads, and these threads will be running parallel in Spark cluster. Now let's assume I am introducing a wide dependency transformation here. Wide dependency transformation. So in that case, what will happen? Because wide transformation output takes input from all the partitions data, we cannot run this wide transformation independently, right? So let's say we are using this wide transformation here. So for this step to execute, we need data from this, we need data from this, we need data from this, and we need data from this, right? To execute these wide dependency transformations, we need data from all the individual partitions. Let's assume we are executing an order by transformation based on a ID column. Okay, let's say our first data partition have ID of 1, 2, 4. Our second data partition have ID of 1, 3, 6. Now third data partition have ID of 3, 7, 8. Fourth one have 2, 4, 6, like that. So in order to do this order by, I have to get the records from all the data partitions, right? Because these IDs are jumbled up in our input data partition. So to execute this wide dependency transformation, I need input from all the data partitions. Because of that, Spark cannot run this wide transformation individually on top of each data partition. So it has to gather the data from all the partitions and then perform this operation. So once this wide transformation is done, it can again break the output into different data partitions. Let's say it breaks the data into 4 output partitions. So it can distribute that into 4 threads, and then again we have narrow transformation which can be applied independently. So from this step again we are good to go with parallel execution, and at the last we have action. So the key takeaway is, to execute wide dependency transformation, Spark needs to gather the data from all the partitions and then execute this wide transformation. Okay, now let's go ahead to our presentation. So this was our stage-wise breakdown of logical query plan. So once we apply this parallel execution concept we just learned, this logical query plan will look something like this. First of all, we have the input data. For simplicity, I have shown here that we have only one partition as input. Now after that we are doing a repartition. As you know that repartition is a wide transformation, and because of that we need to gather the data from all the partitions, and this gathering of all the data and reorganizing this data or redistributing this data happens in buffer. Okay, and this step is known as shuffling of data or shuffle sort. As you may understand that this shuffle sort is a costly operation because the data from all the individual partitions will be transferred across the cluster over the network, right? So this can be a bottleneck. That is why data shuffle or this shuffle sort operation is a costly operation, and we should try to minimize it as much as possible. Now once this repartition 2 is complete, we have 2 data partitions, partition A and partition B, let's say. Now we are applying a series of narrow transformations, that is filter, select, and after that we have order by. So this is a wide transformation. So we have to apply this sequence of narrow transformations in 2 data partitions. That is why Spark will generate 2 threads and it will execute these 2 threads in parallel. So this part can be achieved in parallel. Now at the very last we have order by, right? So order by is a wide transformation. So to execute this order by transformation we again need data shuffling. For that we are using this buffer, and once the order by is complete then we have write. So we will write this data into 2 threads at the storage location. So the main takeaway from this slide is Spark cannot execute these wide transformations individually because one stage's output is input to the next one. That is why Spark has to break logical query plan into stages based on the wide dependency transformation. Now let's check a cleaner version of this flow. So in the stage 1 we have the data from storage layer into data frame, right? And let's say For easier illustration, it has read the data into only single data partition. Now we are applying a repartition too. So in order to apply this repartition too, we have to have this buffer, right? So let's call it write exchange. So these exchanges are part of executor memory. Now after writing the stage 1 output into write exchange, we have to read this data for the next stage, right? So this data movement from this write exchange to read exchange is called data shuffle. And for stage 2, we will be reading the data from read exchange. This write exchange and read exchange can be located at different executors memory. It can be on same executor, but it can also be on different executors. So from this write exchange to read exchange, the data transfer happens through network, and that is why this data shuffling or shuffle sort is a costly operation. So after the data is read from this read exchange, we have two data partitions, right? So we can apply the series of narrow transformations into two parallel threads. These are called tasks. So these tasks will be executed in parallel. Also notice one thing, that the number of tasks will be equal to the number of data partitions at the start of each stage. So in stage 2, I have two data partitions. So because of that, I have two parallel tasks. Let's say Spark breaks the input data into, let's say, 50 partitions. In that case, we can have 50 parallel tasks. Of course, it depends on the cluster resources, the cores available, but the number of tasks will be equal to the number of input data partitions at the start of each stage. And at the very last, we have an wide dependency transformation order by. So to execute this order by, we again have to shuffle the data, right? So for this shuffling of data, we are writing the output to write exchange, and again we are reading this output in the next stage as input from the read exchange. And here from write exchange to read exchange, the data shuffle happens. Now once we read it, we have next action, that is write. Spark will write these two data partitions parallelly into storage location. Okay, so this is the detailed view of a logical query plan. So let's summarize what we have understood in this lecture. Spark driver will break the application code into different jobs based on actions. Now once the logical query plan of a particular job has been created by driver, the driver will break the logical query plan into different stages based on wide transformations. Now within a particular stage, there will be multiple tasks or threads which will apply a series of narrow transformations on different data partitions. So tasks will be running in parallel. Now at the end of every stage, we have a wide dependency transformation. Now in order to apply this wide transformation, we will be having data shuffling or shuffle sort. So these are some of the few concepts which are very, very important to understand before we go ahead. So see you in the next lecture. Thank you. Hello and welcome to this lecture. So in this lecture, we'll try to understand Spark UI with the help of a simple notebook. So let's first create a compute. Create compute. This is the compute name, so that's fine. Now let's select single node because it is fine for this demo. And Databricks runtime version is Spark 3.5. That is okay. We don't need photon acceleration, so let's turn it off. Our cluster is standard D4DS V5 that comes with 16 GB of memory and 4 cores. So this piece of information is important. So we are getting 4 cores and 16 GB of memory in total, and terminate after, let's say, 20 minutes. Okay, so let's create the cluster. Currently the cluster is getting created. So by the time it spins up, let's go ahead and understand how a dataset is processed in Spark cluster. Let's say this is our cluster. So we have 4 cores, C1, C2, C3 and C4, and we have 16 GB of memory in total. Now let's say this is our input dataset. Now generally the dataset size is quite large, so Spark reads the dataset in chunks or in partitions, you can say, and then it processes those small chunks or partitions one by one into the cores. Okay, so let's say this is our input dataset and it has 7 partitions. Spark has created 7 partitions for this input dataset. So externally we cannot decide how many partitions Spark will create out of a input dataset, but we can give Spark some guideline based on which it may create the chunks or create the partitions, but it is not a fixed rule, because there is lot of optimizations going on behind the scene during the execution. So, and in the runtime, Spark can decide how many partitions it wants to create out of this input dataset, based on the input dataset, based on the number of cores and memories available in our cluster, and based on Spark configurations. So let's say our input dataset is partitioned into 7 partitions, P1 to P7, and these are my 4 cores in the cluster, C1 to C4. Now when you submit a Spark job, the input dataset P1 will be assigned to this C1. So this, let's say this is task 1. Okay, now P2 will be assigned to C2, this is task 2. P3 assigned to C3, it is task 3. P4 assigned to C4, it is task 4. So you can see 4 tasks, T1, T2, T3, T4 are running in parallel in C1, C2, C3, C4. That is processing P1, P2, P3 and P4 partitions. Now let's say this task is complete. Okay, so this C1 is vacant, right? This C1 core is vacant. So what Spark will do, it will assign P5 to C1. So let's say this is task 5. Now let's say this task 3 is complete next. So C3 is vacant. So it will assign P6 to C3. Let's say this is task 6. And let's say task 2 is complete now. So C2 is vacant. So it will assign P7 to C2. And this is task 7. So like that, so it will assign each partitions to cores one by one if a core is vacant or empty. So this is how Spark will process partitions, and at a time 4 partitions will be processed together or parallelly, because we have 4 cores, C1, C2, C3 and C4, right? So let's go ahead to Databricks UI to understand the notebook and run the job. So our cluster is up and running. Let's go to workspace, common, and this is our simple notebook. In this simple notebook, what we are doing, we are reading a CSV file from this location, and then we are applying a filter on this data frame, that is firedf, and then we are adding a column with column, and then we are selecting some important columns from the full dataset, and then we are writing it to this location in Parquet format. Okay, we will understand different tabs of Spark UI using this simple notebook. Okay, and one more thing we have done is, like, we have done this set job group, so it will represent these queries in a better way in Spark UI. So this one is read data frame, and this one is narrow transformations on data frame, and then we are writing it, right? So let's run these 2 cells. Okay, now our notebook has finished. So let's go to Spark UI here. The first thing we will check is executors. We know that our cluster has only 1 node and it has 4 cores. So you can see here summary matrices. Active 1 means it has only 1 active node, and storage memory is 4.2 GB. But during creation we saw that the cluster has 16 GB of memory, right? And here it is showing that it is having storage memory of 4.2 GB only. So why is this huge drop in memory? Because most of this memory that is allocated to a cluster is used for Spark's internal operations. Okay, to run the kernel and to use some buffer to run Spark's internal operations, and only a small fraction of the total memory is assigned for users and for user transformation or user query related tasks. So that is why we are seeing 4.2 GB of memory only assigned to user and user related tasks and commands. Okay, now cores, we have 4 cores here, and completed total tasks are 18. So for these 2 queries we have 18 tasks generated, and completed task is 18. So all the tasks has been complete. Okay, now input data is 2.1 GB, and this is summary one. If we want to check the details, we can go downwards and you can see the executors. We have only one executor, that is driver, and this is the IP address of the driver. It is in active state and the memory is same 4.2 GB, and out of which 218 KB has been used. Okay, so now let's go to this SQL and data frame tab. We can see here we have two queries, read data frame and narrow transformation on data frame. So these two queries, read data frame and narrow transformations on the data frame. So this kind of look nice in order to understand the queries and different jobs associated with it. Okay, now we can see read data frame, this query has job ID is 0, so it has created only one job, that is job ID 0. And narrow transformation on data frame, this has created job ID, that is 2. Okay, now let's go to jobs tab to understand this. Here we can see we have 3 jobs, right? Job ID 0, job ID 1 and job ID 2, whereas in the previous tab, that is SQL and data frame tab, we see only 2 queries, and here also only 2 jobs are generated, that is job ID 0 and job ID 2. But in the jobs tab I see 3 jobs. Okay, and this read data frame query has generated 2 jobs. So what is happening here? So why this single query has generated 2 jobs? So we will check it in a bit. And this is the job ID 2 which has been created for this narrow transformation on data frame. So these 3 jobs has taken 2 seconds, 16 seconds and 13 seconds respectively, and these 3 jobs has one stage. You can see 1 out of 1 has succeeded, 1 out of 1 is succeeded, and 1 out of 1 is succeeded for these 3 jobs. And these jobs will be broken down into stages and tasks, right? So for the first job, that is read data frame, only one task is getting generated, whereas for the second job, that is again read data frame, 9 tasks are getting generated, and for the third one, that is narrow transformation on data frame, 8 tasks has been generated, and out of which 8 has been succeeded as well. So let's go to the stages tab once to understand better. So these are the stage IDs 0, 1 and 2, and you can see again for each job there is one stage, that is read data frame and narrow transformations on data frame. And here we can see the input and output size as well. So for the first stage, that is read data frame, we have only one task, right? And it is reading 16 KB. So this looks like it is reading very small amount of data. So it looks like a metadata kind of read, in which Spark just goes to the storage layer and reads the header and the column information of this dataset. So you can see here, let's go inside it. You can see it has generated only one task, that is why process local is 1, and here input size / records. So this is the amount of data this stage is processing. So it is processing 16 KB of data and only 1 record. That means it is reading the header record of the dataset to understand what are the different columns, what are the different data types, maybe like that. So that is why Spark has created this small job to understand the metadata of the dataset. Okay, let's go to stages once again. Now for the next stage, that is read data frame, it is reading 185 MB of data. So it looks like it is reading the CSV file in this stage, and it is taking 16 seconds, and it has generated 9 tasks, out of which 9 has been completed or succeeded, right? So let's go to this once, and here you can see the total time across all tasks is 56 seconds. So this is the total combined time of all the 9 tasks of this stage. Okay, process local is 9, that means 9 tasks are generated in this stage, and input size is 185 MB, and this many records it is processing. Okay, now you can see the same statistics here, tasks 9, so total 9 tasks is generated here, and these are the statistics, task ID 1, 2, 3 till 9, and we can see the executor ID. For us, the only executor is same as the driver, so that is why executor ID is driver. And this is the duration for each and every individual task, 8 seconds, 9 seconds, 8 seconds, like that. And this is the input size, or each task is processing how much input data. So it is, this first task is processing 128 MB of data and this many records. The second task is also processing 120 MB of data and this many records. So like that, for each and every individual task we will get the data size it is processing and the records it is processing as well. So you can see for 8 tasks we have 120 MB of data each, and for the last task, that is the 9th task, we have 61 MB of data and this many number of records. Okay, now these statistics are shown in summarized format in this section, summary metrics for 9 completed tasks. You can see duration minimum is 2 seconds, so this 2 seconds is the 9th one, that is processing the less number of records or less volume of data. 25 percentile is 5 seconds, median is 6 seconds, 75th percentile is 8 seconds, and maximum it is taking 9 seconds out of all these tasks. Now GC time, that means garbage collection time, so it is not significant, it is in milliseconds, so we'll skip it. And the input size, you can see the minimum is 61.2 MB, that we have seen here, right? The last task is processing 61.2 MB, so the minimum is this one. 25th percentile is 128 MB, median is 128 MB, 75th percentile is 128 MB, and the max is also 128 MB. So it seems like Spark is trying to maintain this 128 MB partition size during the read, right? Now let's check the event timeline once. So here each and every individual bar, it represents a task that is being executed in a core. Okay, so in our driver we have 4 cores, right? That is why you can see at any particular point of time 4 tasks will be running in parallel. So if you see here, at this point of time this task is getting ended and the next one is getting picked up here. This is the next one that is getting processed into a core, because the core has finished to process this task, so it has taken the next task that is on the queue. So in this way the Spark will assign 4 tasks parallelly on the cluster, because we have 4 cores in the cluster. So each core will process a single task that is associated with a single partition. So that is the relation. So at any point of time, the number of cores that is present in a cluster, more specifically that is present in the workers or executors, those many number of tasks will be running in parallel. Okay, now we have seen that we have 9 tasks here, right? And we have 4 cores. So up to this point we have processed 8 tasks and Spark has taken the last one from here. So in this time area there is only 1 task is running, that is the last one. Okay, one thing I forgot to mention in the jobs tab is here also we have an event timeline. So here you can see we have this executor, when the executor is getting added, what are the different queries that is getting run at different point of time in the time scale, we can see from here. This small query is like the first one in which we are reading the header, right? And this is the query where we are actually reading the data. Here this is the query where we are doing the narrow transformation and then writing the data. So let's go to stage once again. So this is the metadata query or reading the header record. So this is the stage where we are reading the data actually, and the input size or the input data size is 185 MB. And here in this stage, that is stage ID 2, we are taking this 185 MB of input data, and after processing we are writing only 10 MB of output in our storage area. So why this reduction in size? Because we are doing a filter and we are selecting only few columns, right? So this filter will filter unnecessary records and we are selecting only 4 or 5 columns out of, let's say we have 50 columns here. So that is why the data size is less. So we can see it is evident from here. Our input data set is 185 MB, but we are writing only 10 MB of data in our storage area. Okay. Now let's go to this SQL and data frame tab once, and let's check this individual data frame queries once. So let's check this narrow transformation as an example. So here you can see we have a kind of flowchart kind of thing. So this is known as DAG, direct acyclic graph. So this represent what are the actions that Spark has taken to process this query. So it starts from the bottom. Let's say it is scanning the CSV file here, and if you can expand it, we can see here the size of the file is 185 MB and rows are this much. And number of files read, we have read only single file, that is number of file read is 1. And let's minimize it. So here we are reading 2.8 million records, and then we are having a filter. This filter is represented by this one. And then we are doing a project. Project means it is like select in SQL statement. So select A, B, C column from table 1, right? So this project is projecting all the necessary columns. So this is represented from this statement, select only these few columns. That is why it is using this project. And then we are writing the files. Okay. So this is the last step, that is this write command. So this is known as DAG. And there is another thing, if you go to details, we can see physical plan. So these are the different steps of the plan that Spark will execute, and these are the details of the plan. So first of all, it is scanning the CSV, then it is doing the filter, then it is projecting only the necessary columns, and then it is writing the files, right? So in this way also we can analyze the plan. Let's minimize it. Let's go to SQL and data frame tab. So these are the main tabs of Spark UI, which we will use mostly in our investigation or in our performance improvement. So my cluster has stopped, so I have restarted it. So let's go to the environment tab once. So in the environment tab, you can see the environment related details, that is Java home, Java version, Scala version, all the values of Spark configs, different parameters, all these are present over here. So if you want to check for a particular cluster what is the value of a particular property or Spark config, so you can get it from here. And this is the storage tab. So in the storage tab, we generally get the information what is the size of dataset that is cached into memory of the workers. Okay, so we haven't cached anything, that is why it is showing 00. But if we want to cache some dataset into memory, what is the memory usage for this cache operation, we can see from this storage tab. Okay, the tabs are JDBC or ODBC. So if we have JDBC and ODBC driver running, so those will be shown here. Now next one is structure streaming. So Spark has given a UI for structure streaming as well, but we will not be covering the structure streaming in this course. And then next is connect. So if you have any online sessions or online connections, so we can see from here. So what are the different sessions that is running using this Spark Connect. So these are the main 4 tabs, that is SQL data frame, jobs, stages, and executors to some extent. So these are the 4 tabs that we'll be using primarily for investigation purpose in this course. Okay, so that's it for this lecture. See you again. Thank you. Welcome back. So in this lecture we will understand about Spark query plans. So once you submit a job or query to Spark engine, it will first take the query and the data frames or tables that we have mentioned in the code, and it will first check for syntactical errors. So it will check your code for syntax errors, and if the code is syntactically correct, so then it will create this unresolved logical plan. So after this unresolved logical plan is created, then there is something called catalog, which Spark maintains. It is like a metadata store where Spark maintains what are the different tables or different data frames are there, and what are the different columns, what are the data type of the columns. So all these are maintained in catalog. So once this unresolved logical plan is created, Spark will then take into account this catalog, and it will check whether the columns or data types that you have mentioned in the code is according to this catalog or not. Let's say you are mentioning that select star from table 1. So it will first check the catalog that if there is indeed a table 1, and how many columns are there, what are the different data types, it will check, and it will create a logical plan. Okay, after this analysis it will create a logical plan. So once this logical plan is created, it will then try to do some local optimization using catalyst optimizer. Okay, so let's say you have mentioned that select star from table 1, but in your code you are using only 3 or 4 columns, and in the table there might be 30 or 40 columns. So you are not using all the columns, but you are still selecting all the columns in your query. So what Spark will do, it will intelligently identify that you are using only 3 or 4 columns, and it will read only those columns that you are using in your code. So these kind of optimizations Spark will do, and then after this optimizations has been done, so it will create a optimized logical plan. And then from this optimized logical plan, Spark will create multiple physical plans depending on different algorithms in joins, like sort merge join or broadcast join, like that. So it will create multiple physical plans, and then all these physical plans will go through a cost model which will estimate what are the charges that will be incurred if these physical plans are run actually, and then the most optimized version of this physical plan will be selected as a plan that will be running actually on the Spark cluster. Okay, now from Spark 3.0 there is another feature that Spark has introduced, that is AQE, that is adaptive query execution. What this feature will do, this feature will dynamically adjust the execution plans at runtime based on statistics collected during the query execution. Let's say Spark is reading a large volume of data, and let's say you are joining based on some columns, and it might happen that some partitions are skewed. So because of that, Spark will create multiple physical plans, and then it will apply this adaptive query execution engine to identify and to optimize based on this data skewness or different type of join algorithms. So it will dynamically adjust the execution plan based on runtime statistics, and then it will create a final optimized plan which will be run in the cluster finally. So this is Spark AQE. So let's go to Databricks UI and let's check these physical plans one by one for some sample frequently used operations. Common physical plans. So let me connect with my cluster. Okay, so in this step what I am doing, I am just importing the functions, and then I am setting a job group, and this is the read data frame query I am using in this cell. And what I am doing here, I am just reading this CSV dataset from this location and selecting few columns. There are total 8 columns that I am selecting. This dataset has many other columns, but I am selecting 8 columns because it is sufficient for this demo. So let me execute it. And in the below cell, what I am doing, I am doing this firedf.show 10. That means I am asking Spark to show 10 records from this firedf. So let me execute it as well. Okay, so the cells has been executed. Let's go to Spark UI. So in the SQL data frame tab, you can see there are 2 queries that run. First of one is read data frame, that is the first cell, and second one is show data frame that I am selecting 10 records from the FireDF, right? So first of all, let's go to this read data frame and let's check its physical plan. Let's go to the details. Here you can see the physical plan. Okay, you can see scan text. So in this step, what is doing, it is checking the location, that from this location I have to read this file, and it is checking the schema as well. Okay, so this is just instantiating the data frame. And in the subsequent steps, you can see collect limit arguments is 1. That means it is checking only the header record of this data frame. Okay, so here also in scan text, let me expand it, and here size of file read is 1085 MB. So rows output is 1. That means it is reading only the first record. Okay, that is the header. Number of file read is 1, so it is reading a single CSV file that is present. And once it is done, then collect limit 1. That means it has only internalized the header record. Okay, that is why it is showing as collect limit 1. So it is not a actual job, you can see. Now let's go to show data frame here. So in this case, what I am doing here, I am just firing a query like firedf.show 10. So I am basically asking to show me 10 records from this data frame. So let's go to the details of the physical plan. First step is scan CSV. So it is scanning the CSV file. The output is the 8 columns that we have mentioned in the select query here. In the select query we have mentioned 8 columns, right? So it is checking only those 8 columns. This is the location from which it has to read the file, and this is the schema, call number, unit ID. So it has inferred the schema because we have mentioned here in explicitly like option infer schema true. So it has inferred the schema based on the data available in the dataset. And in the second step, it is doing projection. That means it is projecting all the columns because we have selected 8 columns. In the third step, you can see collect limit, and input is 8 columns and arguments is 11, because we are asking it to provide 10 records. That is why it has taken 10 records and the header. That is why argument is 11. Okay. So in the DAG also you can see CSV, it has read, size of file read is same 1085 MB, and rows output is 11. So because we have asked 10 records, that is why 10 plus the header, that is 11. Now 11 records are read from the storage layer, and then it is projecting based on the columns that we have mentioned in the query, and then it is putting collect limit. Collect limit 11 means, so it is limiting the records collected to 11. That is why collect limit, we have seen that. So this is the typical DAG for .show method. Okay. Now let's do some narrow transformations. So in this cell you can see what I am doing. I am taking this same FireDF that we have read earlier, and I am applying a filter based on this call type column equals to medical incident. So I am filtering only the medical incident related records, and then with column, that means I am adding a new column, address line 1, and how I am defining it, I am splitting the address column based on space and taking the first item or first component. And after doing that, I am selecting few other columns like call type, address, city, unit type, and address line 1. So these are the columns I am interested in. So let me execute this cell. So it has created the data frame. Let's go to the Spark UI to check the details. So let's go to SQL data frame tab, and here you can see narrow transformations on data frame. So this is the one we have run just now. Let's go here and let's check the physical plan. So details, let's check the physical plan. First step is scan CSV. So it is scanning the dataset from this location mentioned over here. And the second step is filter. The filter condition that is applied here is, you can see, is not null call type. So we haven't mentioned this is not null filter, but Spark has automatically implemented this filter as its own optimization criteria. And there is another filter call type, that is medical incident. So we have mentioned this filter. So it is applying two filters based on this call type. One is not null and one is medical incident. And the third step is project. Project basically means like select star from table. So it will project what are the different columns that is getting generated from the last action. So these are the different columns: call type, address, city, unit type, and then it has inserted this split address by space and taking the 0th index item as address line 1. So we have mentioned it here, this line, right? So it has generated the raw code for this column, and you can see that. So input was 4 column: call type, address, city, and unit type, but the output is 5 because we have generated this address line 1 column, right? And you may wonder that the FireDF had 8 columns, right? At the very beginning we have selected 8 columns, but how come here in the project step it is outputting only 5 columns? Because Spark has intelligently checked that we are using only these 5 columns in our action, that is this loop, right? In this select statement we are using these 5 columns, so it is not bothered about other 3 columns, and it has only picked the columns that we are using actually in our code or in the action. So this is how Spark has created an optimized version of the code, even if you forgot to mention something, or even if you might do some redundant work in your code. And the last is the override expression, and it is because of the loop write. You can see loop write, and this is because we have used this action q1df write format loop. We have to use an action to trigger a job, right, in Spark. That is why we have used this loop write. So what it means is like no operations, that is NOOP. So what it will do, it will simulate a write, but actually will not perform a write. So this loop write is very helpful to simulate a write for our benchmarking purpose without wasting any space in the storage layer or doing the actual write. Now let's move on. Next, I'm checking this repartition. So firedf.rdd.get num partitions, it will give us the number of partitions that Spark has created out of this firedf. So let's do this. So it has created 8 partitions of this firedf. Now in this next cell, what I am doing, I am just doing repartition 6. So initially we have seen that it has created 8 partitions. Now I am doing a repartition. So repartition means it will shuffle the data. So let's run this cell. Now this cell has been executed. Let's go to Spark UI. Here, repartition data frame. Let's go to details. Here you can see, first of all it is scanning, then doing the projection, means what are the columns that is required, then doing an exchange. Exchange means shuffling, so it will shuffle the data. In the exchange step, that is 3, it is mentioned that input is 8 columns, these are the columns, and in the argument it has mentioned that round robin partitioning, this is the partitioning scheme that Spark will apply, and 6 is the partition number. So this is the final partition number. So let's understand what is the round robin partitioning in a little more detail. Suppose this is your data frame. So these are, let's say, first row, second row, third row, fourth row, 5th, 6th, 7th, 8 like that. There might be multiple rows here. So round robin partitioning means the first row will go to the first partition, second row will go to the second partition, third row will go to the third partition, fourth row will go to the fourth partition, then again fifth row will go to the first partition, sixth row will go to the second partition, and so on. So here we are doing round robin partitioning of 4, right? So we have 4 partitions, P1, P2, P3, P4. So we are doing round robin partitioning of 4, and that is why we are distributing the data cyclically into 4 partitions. But in our code we are doing round robin partitioning of 6. So it will shuffle the data and it will generate 6 partitions of the repartitioned data frame. Okay. Now let's check the DAG. So first of all, same, it will scan the CSV file, then it will project all the necessary columns, and then it will do the exchange. So in this step it will actually shuffle the data. You can see round robin partitioning 6, that means it will generate 6 partitions. And then this Spark, adaptive Spark plan, so what it will do, it will actually try to optimize the partitioning. What are the different partitioning scheme based on the data, it will try to optimize the partitioning, and then override by expression it will do the loop write. Okay, so this is the sample DAG for this repartitioning. Now after this repartitioning, let's go to colis. So in this cell, what I am doing a colis 4 of this firedf. So what colis will do, it will combine multiple partitions that are present into a same executor, and because of that it will try to avoid the shuffle. So in repartition actually there is shuffle happening, but in colis it will try to minimize the shuffle, or it will try to avoid the shuffle. Let me run this cell and let's check how this colis works. So let's say I have 3 executors, executor 1, executor 2 and executor 3. So in the first one I have 3 partitions, P1, P2, P3. In the second one I have P1, P2, P3 and P4. In the third one I have P1 and P2. So let's say I do df dot colis of, let's say, 3. So what it will do, it will add these 3 locally available partitions into a big partition. So this will be a big partition combining the records from these 3 partitions. Okay. Similarly, what it will do here, it will combine all the 4 partitions available in this executor to create a merged partition, and in this executor it will add these 2 to create a merged partition. So this is for colis 3. Let's say I do a colis of, let's say, 4. So in that case what it will do, so it may merge these 3 partitions into one big partition, then it will merge these 2 as a big partition, and in this case what it can do, it will take these 2 partitions into one, and then it will merge this and this like that. So it will create 2 partitions in this executor. So totally 1, 2, 3 and 4 partitions will be created. So what colis is doing, it is trying to avoid the shuffle, and it is trying to merge different smaller partitions that is present in the same executor to bigger partitions in order to avoid the shuffle. Okay, so in this case you can see there is no shuffling happening because these 3 partitions are present in the same executor, so there is no data shuffling between different executors and different nodes. In this case also these 2 are present in the same executor, and P3, P4 is also present in the same executor, and in the same goes in this executor 3 as well. Now let's see a case where shuffle may actually happen. So let's say I am doing colis of 2 here. So what it will do, so it will combine these 3 partitions, and it will combine these 4 partitions that is available locally, and now there are 2 partitions that is left in executor 3. What it can do, it can take this P1 and it can combine here, it can take this P2, it can combine here, or it can combine both of these to here. So you can see it is trying to avoid the shuffle, but when there is no way, it can result shuffling. So let's check the query plan for coolies. Coolies data frame. Scan CSV, project, and then coolies. And in coolies, you can see there is no scheme available. There is no partitioning algorithm mentioned here. That is because coolies will try to avoid the shuffle. And argument is 4. That is because we are doing this coolies of 4, right? So that is why the argument is 4. Let's check the DAG for coolies. First step, scan CSV, same. Then project, it is projecting all the necessary columns and then doing a coolies. So in this coolies step, what it will do, it will try to merge different small partitions that is present in the same node or same executor, and that is how it will try to reorganize the data and then override by expression. This is loop, right? So these are some commonly used operations. So in the next lecture we will understand some other operations like join, group by, like that. Okay, so see you in the next lecture. Thank you. Welcome back. So this is a continuation of the previous lesson in which we saw different physical plans and DAGs for repartitioning qualies and all this, right? So in this lecture we will understand this physical plan and DAG of joins and group by operations. So let's first understand how this join is performed on Spark. So let's say I have two data frames, df1 and df2, and I'm joining both these data frames based on this call type column. So what Spark will do, Spark will use a function called hash, and it will pass the join key. In this case it is 1, so hash of 1, let's say for simplicity it is 1. Okay, and let's say for our shuffle, the shuffle partition configuration is 100. Okay, so what it will do, it will do a modulo of this hash value with this shuffle partition. So 1 modulo 100 is 1. So based on this result, this record will go to partition 1. Okay, so because our shuffle partition configuration is 100, so that is why we will be having 100 partitions of each of these data frames, right? So the first data frame, that is df1, it will be repartitioned or shuffled into 100 partitions, and the df2 it will also be shuffled into 100 partitions. So this one, so the first record goes to this first partition. The second record, the value, call type value is 1, again hash of 1 is 1, and modulo 100, again we get 1, so it will go to first partition itself. Now this third record, that is 101, so 101 hash of 101, let's say for simplicity it is 101 divided by 100, that is shuffle partitions, equals to 1. So this 101 will also go to this here, first partition. Now the next record, that is 102, let's do hash of 102, and it is 102 divided by 100, so it will give 2. So whenever we do this modulus with this shuffle partition number, so we will be getting only numbers that is between 1 to 100, that is 1 to this shuffle partition number, and that is how we divide the whole data frame into 100 partitions based on this shuffle partition number, right? So this hash of 102 will be 2, so it will go to the second partition, 102. Now this record will also go to this 2. 3 hash of 3 is, let's say 3 modulo 100 modulo 100, it is 3, so it will go here. So like this we will divide this df1 into 100 different partitions, 1 2 3 up to 100 partitions will be there. Similarly df2 will also be divided into 100 different partitions based on this similar logic. So here 1 will be there, 2 will come here, 3 will come here, and 100 will come here. Okay, Now let's zoom in on this partition 1 to understand what is really happening with this kind of reshuffling algorithm. Okay, so for partition 1 the data was 1 1 1 0 1, right? And for this df2 the data was 1 so far. Now suppose for df2 we have a record with call type 101. Okay, so for this 101 record we have again hash of 101 equals to 101 mod of 100, which gives 1. So this 101 records comes also in this partition 1. Using this shuffling mechanism, this 101 record also comes under this partition 1. So you see, whenever we have a particular key in both the data frames, it comes under this same partition using this repartitioning or reshuffling scheme. Okay, so let's say I have a key here 1095. Okay, so for 1095 hash of 1095 equals to 1095 mod of 100 equals to 195. So it will come in the 95th partition over here, right? Similarly for this data frame also, if I have a key 1095, it will come under this partition. So both the records with 1095 key value will come in the same partition. So all the keys of the same value are present in same partition. So it is very easy to join now using these two partitioned data frames of df1 and df2. So after this repartitioning, what Spark will do, it will sort this data frame and sort this data frame internally. This sorting is happened at the partition level. So once these data are sorted based on the key column or call type column, it is easy to do the join, right, using these two data frames. So first of all, it will reshuffle the data based on this hash function, and then it will do this sorting, and it will do the join, right? So this is how the sort merge join works. So I have already started the cluster. Let me run this cell. Okay, so we have read the input data. Now let's go to join section here, and here what I am doing, I am setting this auto broadcast join threshold to -1. This is to avoid the broadcast join, as you may know. So I have set it to -1 so that Spark doesn't go for broadcast join. And so my first data frame we have already read from this input file, and the second data frame I am creating on the fly in this code. So this is my second data frame called df call type, and these are some different sample call types that we are generating. And then in this cell what we are doing, we are joining fire df with df call type based on this call type column. Okay, and it will be an inner join. So let me execute this. Okay, it has finished running. So let's go to Spark UI to check the details. Let's go to SQL data frame tab, join data frame. Let's check the physical plan first. Here is the physical plan. First of all, it is scanning the existing RDD that we are creating on the fly right here. So it is scanning this RDD, and then it is applying a filter. Let's check what this filter is. It is step 8. So let's go to filter step 8, and condition is not null call type. So we haven't mentioned this filter, right, but Spark has inherently applied this filter based on its own optimization. So because this call type is a join key, so it should not be null. So Spark has intelligently put this filter on its own, so is not null call type. Now after this filter, it is doing an exchange. That means it is doing this shuffling, it is doing this reshuffling of data, and you can see the statistics is 152 bytes, and once the data is shuffled, it will then again go and read the data that is present in same executor, AQ shuffle read, and then it will do the sort. So this sort is internal to a particular executor, right? That we have just seen this one. Okay, so it is doing the sort. Similar step it will do for the second data frame, that is scanning the CSV file and then applying the filter. I guess this filter will be similar to this not null. Let's check. Condition not null call type, yes. So it is same. Now it is doing similar exchange, and then it is taking the statistics, and then it will read the data, read the shuffled data, and do the internal sorting. Okay, so for both these data frames it has done similar operations, and after that it is doing a inner sort merge join, that is step 13. You can see left key is call type, right key is also call type, join type is inner. Okay, so now after this join it will project all the necessary columns. What are the different columns that is present in both the data frame? So it will project all the columns, and then it will do the loop write. So let's check the DAG once. So this is the CSV data frame. So it is first scanning the CSV file and then applying the not null filter and then doing the shuffling. You can see hash partitioning. So it is using the hash function that we have mentioned here. Hash partitioning. You can see call type, comma 200. 200 is the default shuffle partition number that Spark use. So if we don't provide any shuffle partition number from outside, Spark will take 200 by default. Okay. Now after this exchange, what it is doing, AQ is reading the shuffled records and then it is doing a sort, and then this sort merge join is happening. Let's check the other branch as well, that is the existing RDD. It has taken 4 records because it has 4 records. And now it is applying the not null filter, and then it is doing the same exchange hash partitioning based on call type, and the shuffle partition number is 200. So we can check this by expanding this box as well. So you can see number of partitions is 200, and after doing this, what it is doing, it is reading the shuffled data. So number of partitions is 3. So AQE has already identified that there are multiple empty partitions because our dataset has only 4 records and the shuffle partition configuration is 200. That is why there are multiple empty partitions. So that is why Spark has coalesced those empty partitions and created 3 final partitions with data. Similarly for this branch as well. So it has taken it has coalesced other partitions and it has produced only 3 partitions. So now these 3 partitions will be sorted internally. You can see sort call type ascending nulls first. Okay, so similarly for this as well, call type ascending nulls first. Now after this is done, it is doing the sort merge join, and then it is projecting the necessary columns. Okay, and once it is done, it is just checking the statistics that size in bytes is 2.3 GB, row count is this much, and then it is doing the loop write. So this is a sample DAG for sort merge join. So let's move to the next operation, that is group by count. So here what I am doing, I am grouping by based on this call type, and I am trying to get the count based on this group by condition. Okay, so let's run this. So by the time it runs, let's go in the whiteboard and let's understand how this group by operation works. So let's say I have data in these 5 partitions, P1, P2, P3, P4, P5, and I have taken some sample data only so that it is easier to understand. So here you can see for P1 there are multiple call types, let's say alarm, medical and other. So in order to do this group by count operation, so what Spark will do, it will create a partial count of the records that is available in a particular partition, and it will generate a summarized count. So let's say for P1 the alarm count is 2, medical count is 1, other is 1. For P2 medical is 2, other is 1, alarm is 1. For P3 alarm is 1, other is 2. For P4 medical is 1, other is 2. For P5 other is 1, alarm is 1. So now once it has generated this partial count for each and every individual partition, it will combine these counts. Because these counts are in summarized format, so what it will do, it will cause less data shuffle. So the data shuffling will be less. Because of that, Spark first do a partial count, and then it will collect this partial count from each partition, and then it will combine it together. So for final counts, it will produce like A2, 3, 4, 5. So A is 5. For medical it is 1 plus 2, 3 plus 1, so it is 4. And for other it is 1 plus 1, 2 plus 2, 4 plus 2, 6 and 1, 7. So this is the final count. So this is how Spark will calculate the group by count. So let's go to our Spark UI to understand this. So the job has already run. Let's go to the Spark UI and check this group by. Here you can see scan CSV, so it is scanning the CSV file, and hash aggregate, so it is doing aggregation. Let's check this hash aggregate 2 once. You can see here 2 hash aggregate. In keys are call type, and function, in the function you can see partial count. That means it is counting the records that is present within the same partition. Okay, so that is partial count. And once the partial count has been generated, so you can see statistics, the row count is 243 and size in bytes is 11 KB, so it is much less data to do shuffling. So now after this shuffle stage, the AQ will read from different partitions and then it will hash aggregate. So this hash aggregate 6, this should be a final count. So let's check hash aggregate 6. You can see 6 hash aggregate here, and functions final merge count. So it will merge all the counts from different partitions and it will produce a final merge count. Okay, now let's check the DAG once. So similar drill. First of all, it is reading the CSV file, then it is doing a hash aggregate, and it is function is partial count, and doing the exchange. Similar to previous one, the shuffle partitions is 200 by default. Now AQ will read these different partial counts and it will produce the hash aggregate, and this one is final merge count. So this one is kind of combining all the counts from different partitions and it is producing a final count. So this is how this group by count operation DAG looks like. So that's all for this lecture. Hope you have understood it. Thank you. Welcome back. In this lesson, we will understand about schema inference overhead problem. Now this problem is associated mainly with the spark.read operation. So what we will benchmark? We will benchmark spark.read operation for different file types. As you may know that spark.read is a lazy operation. That means when we execute spark.read, it will not go and read the data from the directory, right? At that point of time, it will just instantiate the data frame, and to instantiate the data frame, it needs two information: what is the data location and what is the schema of the data. So these two information it needs, and it will just instantiate the data frame when we execute the spark.read operation. And after, when it comes across an action, then only it will actually go and read the data. So spark.read is a lazy operation. What is the cluster size that we are going to use in this experiment? We will use single node standard D4DS V5 cluster, that is 4 core and 14 GB of memory. What is the data volume that we will be dealing with in this lesson? As we mentioned earlier, that we will be dealing with different file types with various volumes. So we will be dealing with Parquet dataset, roughly 12 GB of volume. We will be dealing with JSON dataset, roughly 6.5 GB of volume, and we will be dealing with data dataset with 12 GB of volume, and then we will compare the results of how fast Spark is reading this spark.read operation. And let's go ahead to the UI to do this experiment. Here is my compute. It is single node compute, as you can see, standard D4DS V5 that comes with 16 GB of memory and 4 cores. So I'll start this cluster. And this is the notebook we are going to do experiment with. So let's wait some time to start this cluster. It has started. So let's go through the notebook one by one. So in the first cell, what we are doing, we are reading Parquet data from this directory. So let's execute it. In the next step, what we are doing, we are reading JSON data from this directory. Let's execute it again. And in the third step, we are doing delta data from this directory. So let's wait for some time to execute these operations, and then we'll head to the Spark UI to understand little detail what is happening. The cells has been executed. So as you can see, the first cell, that is reading Parquet data, it took 8 seconds. The second cell, that is reading JSON data, it took 1 minute, maybe more than that. And the third cell, that is reading delta data, it took 2 seconds. So let's go to the Spark UI to understand a little more. So here you can see Q1 read Parquet without schema, that is this cell, right, reads Parquet without schema. So here you can see it took 2 seconds, the job took 2 seconds, and only one task is initiated. But read JSON data without schema, it took 1 minute and 54 tasks has been initiated. So why it took 1 minute and why the Parquet did in 2 seconds? So the reason is that the Parquet data set comes with data and the schema. So the Spark engine just needs to go to the directory and read one Parquet file to understand the schema and the columns and the data types. So that is why it has initiated only one task, so to read only one file. But when we are reading JSON data, the JSON data comes with columns, but it doesn't have any data type inbuilt in the file, right? So Spark needs to read the whole file or maybe a sizable portion of the file. That is why it is taking 1 minute to read half of the size of the data, and it has initiated 54 tasks for them. And you can see we have run the delta read operation also, but here we don't see any job for the delta, because the delta dataset, the delta table comes with data and the metadata inbuilt in it. So Spark doesn't need any extra overhead to read the metadata, to understand the data type and the directory. It can directly go to the metastore and read the metadata from there. So that is why Spark didn't initiate any extra task to read the metadata of this delta dataset. So that is why there is no job associated with the delta read. Now let's go ahead and verify the data volume of each of these 3 file types that I mentioned, right? So here we have executed an action so that we can verify the data size. So let's execute these three cells and we will verify the data size. First one is writing the Parquet data, second one is writing the JSON data, and third one is writing the Delta dataset. So let's wait for these to complete and then we'll analyze the file size of these three datasets. Okay, the write query has been finished executing. So let's go ahead to the cluster and let's find out the details of the volume of the data that we processed. So here in the SQL data frame tab, you can see Q1 write Parquet without schema. It took 2.2 minutes. So let's go here and let's see what is the data size. So you can see size of file read is 12 GB, around 12 GB that I mentioned in the PPT, right? Now let's go to the another one, that is JSON data. What is the size of this file? Let's see. Input read total data size, that is 6.5 GB around. And let's verify the delta one as well. Scan Parquet. So here you can see input read data size is 11.9 GB, so around 12 GB. Okay, so indeed you can see the JSON data is half the size of other two datasets, right, Parquet and Delta. But in spite of that, it took 60 seconds to run this read query, right? This 1 minute is reading this JSON data. So why it took 60 seconds? That is because the schema inference overhead that I mentioned, right? So JSON data doesn't come with schema inbuilt in it. So that is why the Spark has to go and read sizable portion of the file or maybe the full file to understand the columns and data types of the data. So what we can do about it? How we can eliminate this extra time that Spark takes to read the JSON data? So it is simple. Just we mention the schema beforehand to Spark, and Spark will not read the files to get the schema. So let's do that. So here we are defining the schema. This is the schema of the files, and now let's execute those three operations as well. Here you can see in Parquet it took 2 seconds, and in JSON it took less than 1 second, and we have mentioned the schema explicitly, so it doesn't need to go to read the file and infer the schema. Same as JSON, same for JSON as well. Since we mentioned the schema beforehand and explicitly to Spark, it doesn't need to go and do the extra overhead and extra work to infer the schema by loading the files, right? So that is why it took less than 1 second to instantiate the JSON data frame. So from 60 seconds to less than 1 second, that is the magic. So you give the schema and Spark doesn't need to look at the file. So if you go here, cluster details, if you refresh it, you can see there is no job associated with reading these files again. So we have run this spark.read operation, right? But it doesn't trigger any job because we have given it the schema explicitly. So it doesn't need to go and trigger a job to instantiate the data frame. So it already has all the information. It has the schema and it has the location of the directory from which it has to read the files. That is why it processed the read operation much faster. So what did we learn here? We learned that schema scan is an useless overhead for Spark engine. So it generally takes time, but it doesn't add any value to the Spark job, right? So reading data should not create any extra jobs. So if you see that reading the data is creating an extra job, as we see here, reading JSON without schema, like this: load at native method, load at native method. So this means the Spark is creating extra job to load the file, to instantiate the data frame, to know the schema, to understand the schema, like that. So it is an extra overhead. So reading data should not create any extra job. You can detect schema problem scans with the presence of an extra job in reading data. So as we have seen in the Spark UI, right? So you can detect it from there. You can avoid schema read scan with the following ways. What are the following ways? First of all, always use schema while reading data from file sources, and it will not go and analyze the files to get the to infer the schema. Create external tables for reading data from file sources. When we create external tables, we are telling Spark engine two things. Where the table is located, means at which directory the table is pointing, the data of the table is pointing, and the second one is what are the different data types and columns of the file. So if we create an external table, Spark will easily go and read the metadata from the metastore, and it will not infer the schema from the directory. Okay, so it is always a good practice to create external table to read a data file from file sources. Otherwise, what we can do, we can use delta to minimize the overhead. As we know, delta comes with delta tables comes with metadata. So if we read the data from delta, Spark engine will read the metadata from the metastore, and it will not even check the data. So that is how we can minimize the overhead. So that's all for this lecture. Thank you and see you soon. Welcome back. So in this lesson, we will understand a problem that occurs during reusing the same data. So let's understand a problem. So suppose in your company you have an application team. They came up with this problem statement that they are creating a data frame and executing multiple queries on top of the same data frame. So they are basically reading data from a storage location, and they are executing multiple queries on top of the same data frame. But they are saying that, however, our queries are running slow. So they have a problem that they think their queries are running slow. So they investigated the query plans of each and every individual query, and they noticed that Spark is recreating the data frame for every query and reading it again from the storage. So let's say they run 5 queries on top of the same data frame. So they are saying that Spark is reading the data 5 times from the storage location and then executing the query on top of the data. That is why they believe it is running slow. So this is the problem statement. So why the Spark is reading the data again and again from the same directory. So here are their questions. Why Spark is reading data again from each query? So this is a genuine concern, right? Because Spark is an in-memory computation engine, so it should read the data once and keep it in memory, and then if we execute multiple queries on top of that, so it should take the data from the memory. It doesn't need to go and read the data again and again from the storage location. So why Spark is doing this? So this is causing the job to run slow. Second is how we can reuse the same data frame to optimize the performance of our queries. So they want to read the data once from the storage location and keep it in memory, and then reuse it again and again for their let's say 5-10 queries, so that it doesn't need to read the data again and again. So how we can reuse the data to optimize the performance of their queries. So what do we want to benchmark here? We want to benchmark and observe the behavior of multiple reads, as my other teammates are saying that they are seeing that Spark is reading data again and again. So we want to validate it. Okay. Now after validation, what if it is true? After validation, if it is true, we would like to find a solution to reuse an in-memory data frame so that their queries can run faster. So what is the cluster size that we are going to use in this experimentation? we will be using the same single node cluster with 14 GB of memory and 4 core that we used in the previous lesson. What is the data volume? Data volume will be 1 GB CSV dataset. So it is enough to demonstrate this use case. Okay. So let's go ahead to the Azure Databricks UI and let's do the experimentation. So this is the notebook we will be using, reusing data frame before, and our cluster is ready. So we have connected the same single node cluster. First of all, we will be disabling the disk cache. So let's execute it, and then we will be reading the data of CSV format from this location, and then we will be executing 4 or 5 queries on top of that data, and we will understand if it is true that Spark is really going to read multiple times. So here is the first query. You can see Q1 df. It is executing the query on top of the fire df. Fire df is this one that we have read from this location, right? So Q1 df is executing the query on fire df. Q2 df is executing the query on fire df again. Q3 df is executing the query on fire df, and Q4 df is also executing the query on fire df. So all the 4 queries are executing on top of this fire df that we are reading from this location, and we have associated action at the end so that we can validate the jobs and the results. Okay, so let's run all and let's wait. So all the 4 queries has been finished. You can see we have run all the 4 queries, and let's go ahead and move to the Spark UI to understand what they are claiming. So here you can see the 4 queries. Read the data frame. This is the first query, and this is regarding this one, reading the data frame. And run Q1, run Q2, run Q3, run Q4. These are the 4 queries they have run. So let's go to the run Q1 first and understand from where the data is coming. So in this version of Spark, you can see it the DAG is from bottom to top. So let's go to the bottom, and you can see scan CSV. So in this step, it is scanning the CSV data from the location or directory, right? So you can see here, so it is scanning approximately input read total data size is 1000 MB, 1085 MB, so approximately 1 GB. So it is reading the data, and it is reading 4.3 million records, right? So this is the read part. Now let's go to the Q2. So here also you can see scan CSV. So here also I see that input read data size total is 1085 MB. So it is indeed reading the data multiple times, and you can see size of file read is also 1085 MB. So it is indeed reading the data multiple times for Q2 as well. Now let's go to the run Q3. So it should be similar, that it is also reading the data from the file, right? So you can see here input read data size is same 1085 MB. So every time it is reading the data from the directory, right? So their query or their concern is correct. So it's reading the data multiple times from the directory for each and every query. So why it is happening? So let's go to the notebook and understand. So when we are executing this cell Q1 df, so it is getting triggered by this write action. So write action is on Q1 DF. To calculate Q1 DF, it needs to have the fire DF. So for fire DF, it is going here and reading the data. So again for Q2 write, it needs this fire DF, and then again it backtracks and it is going to this fire DF, and it is again reading the data from this location. So for this reason, for this backtracking reason, it is multiple times going to the same fire DF and reading the data from the directory multiple times, which is unnecessary, right? So we can load the data into memory if we are using it multiple times. So to navigate this situation, to fix this problem, what we can do is we can explicitly tell Spark that we will be using this fire DF multiple times. So please cache it in memory, cache it in your memory. So then only Spark will understand that it needs to cache it in the memory, and after that, whenever you are using this fire DF, it will read the data from the memory instead of the scanning the data from the directory. So for that, let's go to the after using data frame after notebook. Here you can see we have used firedf.cache. So if we use this statement cache, we are explicitly telling Spark that please cache this data frame, because we are going to use it multiple times in the later phases of the job or application. So Spark will understand, and Spark will note that we need to cache it. And then when we will be executing these queries, it will read the data once from the directory and cache it, and for the subsequent queries it will read the data from the memory, not from directory. The processing will be much faster. So let's execute this notebook and check out the details. So the notebook has been finished. Let's go to the Spark UI and understand the details. So here, so these are the later queries from the after doing the cache. So reading the data frame Q1, Q2, Q3, Q4. So you can see here, reading the data frame is taking 0.4 second. Run Q1 is taking 33 seconds, whereas previously run Q1 was taking 8 seconds. So as you know that Spark cache is a lazy operation. So when you say that firedf.cache, it will note that it need to cache the data frame, but it will not cache it at that point of time. When we are going to use it with an action, it will cache it. So first we are using it. So here you can see, when we have mentioned here firedf.cache, it will just note that it need to cache it some point of time. But when you are running this Q1, actually we are using this firedf, right? So at this point of time, it will cache, it will execute this cell, and it will cache the data frame. That is why it is taking 33 seconds. So first time it is caching the data. That is why it is taking more time, and that we can validate from here as well. Run Q1 is taking 33 seconds here compared to run Q1 previously 8 seconds, because caching is an expensive operation, so it takes time to cache the data. But you can see that run Q2, run Q3, run Q4 has taken previously 8 seconds, 6 seconds, 6 seconds, but here after the cache operation, run Q2, Q3, Q4 has taken 1 second, 0.5 second and 1 second. So it is much faster because it is taking the data from the in-memory cache, not reading the data again from the directory. So let's go ahead and let's validate the DAG from these runs. So here you can see Q1, run Q1. So runs scan CSV. From scan CSV you can see it is reading input read total data size is 1085 MB, same as before. Okay, and it is reading 4.3 million records, and then it is doing this in-memory table scan. That means it is caching the data in memory. Okay, so you can see here details. Scan CSV and then in memory table relation, that is 2. Here arguments, these are the columns of the data. So it is loading all the data into its own memory, Spark's own memory. And now let's go to Q2 and let's see why it is taking less time. So let's go to run Q2. Now you can see it is doing scan CSV, but it is generating 0 records. So it is doing a dummy scan of the directory and generating the records. Here you can see in memory table scan, it is generating 4.3 million records, same as before. So it is just doing a dummy scan from the directory, and instead it is taking the records from the in memory table scan, and that is why the queries are getting faster. Means the data is already present in memory, so the queries will be running on top of the data that is loaded in the memory, and so it is running much faster. So that is why it has taken less time. All the subsequent queries has taken less time. Run Q3, run Q4, every query it will be taking the data from the in memory table scan. You can see in memory table scan, it is generating same 4.3 million records, and scan CSV, it is a dummy operation kind of thing, it is generating 0 records. So what did we investigate? We investigated that check query execution time, and we compared the query execution time before and after the caching operation. So it has improved drastically. And we have also checked that input read data size. So first of all, before caching, we are reading data 4.3 million data every time from the directory, but after caching, the first query will read the data from the directory, and all the subsequent queries will be reading the data from in memory cache. So that also we have validated, right? So what is the conclusion here? Conclusion is reusing data frame requires caching. So if you want to reuse a particular data set or data frame multiple times in your application, you need to cache it explicitly. Caching is an expensive operation, and it costs memory and time to cache. So as we have seen that caching data take 33 seconds here. So it is an expensive operation. So we don't generally cache a data if we are using 1 or 2 times. So if we are using a data set maybe 5, 6, 10 times like that, so we generally cache it. So cache when using a data frame multiple times, typically more than 3 to 4 times, then only caching makes sense. Otherwise the effort required or the time required to cache the data will not be justified. So that's all for this lecture. So see you again in the next lecture. Thank you. Welcome back. So in this lesson, we'll understand column scan issue with a problem. So let's understand the scenario first. So we have a team. So they are saying that they are reusing data frame multiple times and hence cached it. So from the previous lesson, they have learned that if you want to reuse a data frame multiple times, we should cache it, and they have actually gone ahead and cached it. However, the first query on the data frame is taking longer than expected due to caching. So in the previous lesson, we saw that when we are executing the first query on the data frame, so it will actually go and cache the data. And this first query, they are saying that it is taking longer than expected. So they are concerned about the first query. So they have few questions like, are we caching too much data on our workers? So as the first query is taking longer than expected, so they are worried that they might be caching too much of data on their workers, and it might cause memory overflow, or it may cause shortage of memory in the subsequent steps and transformations. So do we have sufficient memory to cache the data? So next is, can we improve the latency of the first query that performs caching? So they are concerned about the first query that it is taking longer, and that is why they are asking if the latency of the first query can be improved so that it performs faster. Okay. So let's go ahead and let's see what we want to benchmark here. So we want to cache the data frame and run multiple queries on the cached data, and see how it is performing. What is the cluster size? Cluster size is same single node cluster that comes with 14 GB of memory and 4 cores. What is the data volume? Data volume is approximately 1 GB of Parquet dataset. Now let's go ahead to the Spark Databricks UI and do this benchmarking. So here is the notebook column elimination before. Let's open it, and my cluster is running. So let's go ahead and execute the cells. So first of all, I am disabling the disk cache and then reading the data from this location and caching the data. Okay, and after that I am running two queries. This is the first query, filter and write, and this is the second query, group by and write. Okay, so they are worried about this first query, that is this filter and write, in which we are caching the data actually and filtering it based on the stored location and selecting few columns. So they are saying that this query is taking longer than expected, and if it can be improved, the timing of this query can be improved or not. Okay. So let's wait for some time to finish the execution of these actions. One thing I forgot to mention in the previous lesson, that if we are caching a data frame, so we have to uncache it explicitly as well. So it is the responsibility of the user to uncache the dataset. Spark will not uncache it, and as long as you don't uncache it, it will stay in the memory. So it might cause memory related issues later down the line. So when you are doing the queries with the data frame that you have cached, you should explicitly uncache it. Okay, so that is why this statement is here, but I have not run it because we will be doing some experimentation and we will be checking some details, and after that I will be uncaching it. So the cells have run. So you can see the first query, that is filter and write, it took 57 seconds to cache the data and filter this data based on the query, and the next query took 4 seconds. So let's go to the Spark UI to check the details. Let's go to the SQL data frame tab, and here are the two queries. The first query is filter and write, in which we saw that it took 56 seconds approx, and this is the query where the data is getting actually cached, right? And the second query took 4 seconds because it is operating on the cached data. So before moving into these queries, let's go to once the executors tab. Because it is a single node cluster, you can see only one executor is there, that is working as driver and worker both, and because of that the storage memory is 1.3 GB out of 4.2 GB. That means we have used 1.3 GB of memory of this driver because of the caching that we performed here out of this 4.2 GB. And if you can go to the storage tab here, you can see disk memory deserialized. This is the storage level, and the size in the memory is 1294 MB. So that is approximately 1.3 GB that we saw in the executor step, right? And the fraction cached is 100%. So this is also important, because from this percentage we know that our 100% of the data is cached. Okay, so if let's say this fraction is not 100%, let's say it is 50%, and in future our query pattern changes, so Spark will cache other portion of the data as well that are getting hit with the new query pattern. So because of that, the size of the memory might increase if this cache percentage is not 100%. So because it is 100%, we are making sure that this size in memory will not increase much even if the query pattern changes in future. Okay, so this is one check we need to be aware of, to be doubly sure and to be safe, so that our caching doesn't cause any memory related issue. Okay, so we have checked that the size of the data we cached fits in the memory, so it is not causing any problem per se, but depending on the operations or the transformations that we do later down the line in the application, it may cause some memory bottlenecks, because it is using approximately 1/3 of the available memory, right? 1/3 or quite a significant portion of the available memory. So this is one thing we need to be aware of. Now let's go to the notebook and let's see how we can optimize it. So you can see, if we dig deeper, we can see that here we are dealing with some handful of columns like store location, transaction ID, total price, product category. These 4 columns we are dealing with, right, in our queries, but we are caching the full data, and this full data set might have, let's say, 20 or 30 columns, but we are dealing only 4 or 5 columns in our queries. So we are unnecessarily caching the full data, whereas we could have selected only 4 or 5 columns that we are using in our query and cached only those portion of the data. So the cached data will be less, the jobs will run faster, and the memory utilization will also be little less, right? So let's go ahead and let's try to tune it. So this is the column elimination after. You can see here I have selected only those columns that we are using in our query: store location, transaction ID, total price, and product category, because we are using only these 4 columns, and after that we are doing cache only with these 4 columns. Okay, so let's run the cells and let's see if it improves the performance or not. So the cells have run. So you can see here the first query that is actually caching the data, it has taken 17 seconds. Previously it took 57 seconds, so that is quite improvement we can see here. And the second query also ran faster. It took 4 seconds previously, now it is taking 2 seconds. Let's go to the UI and let's validate these data. So here you can see the first 2 queries, that is before the optimization, the cache took 56 seconds and the second query took 4 seconds, whereas after the optimization, after we eliminate the unnecessary columns, the caching took 17 seconds and the group by took 2 seconds. Okay. So now let's go ahead and let's see these 2 DAGs one by one. So I'll open these 2 in separate tabs. So this is the before the optimization. You can see scan Parquet, the data input read data size total is 786 MB, and it is reading 20 million records. Now after the column elimination, you can see, let's check what is the data size it is reading from the storage. It is reading input read data size total, that is 380 MB. So it has reduced drastically, so from 786 MB to 380 MB. So it has been almost half the data we are reading, and we are eliminating the other columns. So because of that, caching took much less time, but you can see the number of rows are exactly the same in both the cases, that is 20 million, because when you are selecting columns, we are eliminating other columns, not rows. So the number of rows stays the same, but we are eliminating other columns. So that is why number of rows read is 20 million. That is same in both the cases, 20 million here as well and 20 million here as well. Now let's check the details of the caching. So here in the details tab, in the details section you can see in memory relation to. Here you can see transaction ID, transaction date, transaction time, customer ID, all these columns are getting cached, and this hash number part is like these are Spark assigned column IDs, that is internal to Spark. This is not actual column IDs. So this is the column name is the transaction ID, transaction date, transaction time, customer ID, and so on. So you can see here So before the optimization, we are caching all the columns available in the dataset. So it might have 20, 30, 40 columns. So we are caching all the columns. But we might not need all the columns, because we have seen that in our query we are using only handful of maybe 4, 5 or 10 columns. So optimized version, let's check this part. In memory relation is 2, and you can see arguments are store location, transaction ID, total price, and product category. So these are the 4 columns we are using in our queries, right? So we have managed to limit the number of columns that we are caching, and hence the caching query is running faster. It is caching lesser data. That is why the memory we are using in the driver is less. We will validate that in just a minute. So let's go to the cluster details here, and let's go to the executors here as well. So first of all, as we are running these both the notebooks in the same cluster, previously this storage memory was 1.3 GB and now it is 1.7 GB. So the delta part is around 450 MB. 450 MB. So we are caching here 450 MB of data, whereas previously we are caching 1.3 GB of data. So that means we are utilizing less memory in the optimized version, that is 450 MB. So let's go to storage tab. Here also you can see for the first query, first caching, we are using 1.3 GB of data around, but in the second query we are using 460 MB of data. So that is we have managed to limit the memory utilization that is required for the caching purpose. So that is really helpful. That will free up the unnecessary memory we allocated during caching the unnecessary columns. So our job will have more memory to process the data down the line, do shuffling and joining and all that. So that is a clear improvement. So let's go ahead and go to the presentation. So investigation, check executors tab to see memory used for caching data. We have seen before and after as well. So what is the memory used for caching? We have also checked the cache percentage, and in both the cases it is 100%. Check SQL data frame tab to collect execution time. So we have checked already that before optimization it was taking 57 seconds, and after optimization it is taking around 17 seconds. Check physical plan. We have checked the physical plan, and we have checked even though the number of rows are same, the data volume is before it was 786 MB around, and after it was like 360 MB most likely. So it is reading much less data in the optimized version. Check your cache query execution plan for scan details. So we have checked the execution plan as well. So rows output and input read data size. So we have checked all these things. So what is the conclusion from this lecture? Conclusion is prefer using columnar file formats such as Parquet or Delta. So why we are able to eliminate the columns? Because Parquet or Delta, these are columnar file formats, and fortunately we are using Parquet dataset here. That is why we are able to eliminate all the unnecessary columns and only load the necessary columns in the memory. So this is the beauty of columnar file format. We can eliminate the columns that are not necessary, that we are not using in our application, and we can only deal with the columns, selected columns that we are using in our application. Select or cache only required columns instead of all columns. So we have clearly seen that it improves the result quite a bit across all fronts, like time, memory, size of file read, everything is getting improved. So that's all for this lecture. So see you again in the next one. Welcome back. In this lesson we will understand an issue called row scan issue. We will understand it with a problem. Let's see the problem statement. So we have a team, and the team is reading data from table. So they are saying that they have applied filter condition and read small fraction of the table. So they are not reading the full table, they are applying a filter condition to read a small portion of the data from the large table. However, the time taken to read the small amount of data is almost same as the time taken to read the full data. So they are saying that even though they are reading a small fraction of the data from the table, the Spark is taking much longer time, almost as long as reading the full table. So this is the problem. So although they are reading small amount of data, it is taking a lot of time. Here are their questions. How can we achieve linear scalability in the filter query? So linear scalability means if we are reading, let's say, 1/10 of the data, so the time taken should be 1/10 of the full volume read, right? So this is called linear scalability. So they are wondering how we can achieve this linear scalability, because they are reading small amount of data from a large table, so they expect that the time to read such small amount of data should be much less than time to read the whole table. So how they can achieve this linear scalability in the filter query? So let's see what we need to benchmark. We will create a temp view and run filter queries to investigate how the filter is being applied. We'll create a temp view on the full data and we'll run filter queries to investigate how the filter condition is applied and how the data read from the storage layer is getting executed, and if we can optimize that process. What is the cluster size that we are going to deal with? We will be dealing the same single node cluster that comes with 4 core and 14 GB of memory. What is the data volume? Data volume will be 12 GB of Parquet dataset. Okay. So let's go ahead to the Azure Databricks UI to perform this benchmarking. So this is the notebook, row elimination before. So I've already started the cluster. It is still spinning up. By the time the cluster spins up, let's go through the notebook. So here you can see we are reading the Parquet data from this location, and we are creating a temp view sales table, and then we are selecting star from sales table. So in the next query as well, we are selecting star from the sales table, because this query is reading data and selecting star, so this may be taking some overhead. So again we are doing the select star from sales table to get the actual time to read the data from sales table. Okay. And then we are doing the same select star from the sales table, where we are applying some certain conditions. This year of transaction date should be 2021 and month of transaction date in 10, 11, 12, that is October, November, December. So this data should be quite small compared to the whole table. So let's see how we can improve this read filter data query. So the cluster has already spun up, so let's run all the queries one by one. Let's wait for some time to read the data and finish the notebook. Then we'll go to the Spark UI to investigate few things. So the notebook has finished running. So let's go to the Spark UI to understand few things. Let's go to the SQL and data frame tab. Here you can see this is the warm up, the first one. It has took 2.5 minutes to warm up, to this warm up. This is the metadata query, 66 milliseconds. So this is most likely a metadata query, so we will not concentrate on this one. This is a very insignificant amount of time. So this is the main warm up where we are reading the data from the table, and it is 2.5 minutes now. So this query, first one. Now the second one is the we will be comparing with. So the second query is the base or benchmark we would be taking. So it has taken 1.5 minutes. Okay. The third one, that means the filtered one, this one, it has taken 59 seconds, so almost 1 minute. So let's see how much data we are reading in these two queries. So we'll open this in new tabs, and this one as well. So here you can see we are reading 320 million records from the scan Parquet step, which is reading data from the storage layer, and which is scanning the Parquet file from the storage layer, and it is generating 320 million records. You can see the file size is size of file read is 12 GB, around 12 GB file we are dealing with, and rows output is 320 million, and number of files read, it is 1280. So 1280 files we have read. So the base query has 320 million data, so we are dealing with 320 million data. Let's see how the filter query is performing here. So this is the filtered one. Here also you can see we are reading number of files read is same 1280 files, and the number of rows output is same as previous 320 million, and size of file read is 12 GB. So same data it is reading. Now after reading the same data, it is generating the same 320 million records, and now it is filtering out in this step. So in the filter 320 million records are going, but out of the filter coming only 16 million. So most of the data is getting filtered out. You can see in the filter rows output is 16 million something. So we are filtering out almost 95% of the data. So is there any way we can minimize the data read from the storage layer so that the time taken to read the data will be minimal? So there is a way. So let's go ahead to the notebook and let's see how it can be possible. Let's go to the optimized version, that is row elimination after. Here what we are doing, we are segregating the data by year and month, because the third query here it is filtering based on year and month column. So what we can do, we can partition the data based on these two columns. Okay, partitioning a data means let's say you have a 1 TB of Parquet dataset, and it consists all the historical records of, let's say, last 5 years. Now generally we process data maybe year wise or month wise, so the data read size is generally for a particular year or a particular month of a year. So in those scenarios what we do, we segregate the data based on different year, different month, so that if we are processing a query where we need to filter out, we need to check only records from a particular year or particular month, or let's say if a demographic data has age column and we are dealing with certain age groups, we want to check how they are behaving or what is their food patterns, like that. So in that way we can segregate the data into different partitions or buckets, you can say, and then when we read the data, we will be reading the data only for those partitions or buckets in which we are interested in. So let me show you the input data, how it looks after the partition. This is the input data, sales data Parquet, partition year month. So you can see year equal to 2019, year equal to 2020, 2021. So it is broken down based on different years, and if you go inside a year, you can see different, it is broken down further based on different month as well. So 1, 2, 3, 4, based on 12 months it has broken down the data. So now if we run this query, year equal to 2021 and month equal to 10 to 11 and 12, so it should pick only 2021 data, this folder, and month 10, 11 and 12. So it will be reading much less data. So the number of data files read will be much less, the size of files read or volume of files read will be much less. So we can minimize the reading of the data from the storage layer to Spark memory. So let's see how it works here. So let me learn all the cells here and then we will analyze. Okay, the query has been finished. So let's go to the Spark UI to understand this case how it is working. Let's go to the SQL and data frame tab, and these are the 4 queries, that is after the partitioning or after the optimization has been done. In the partitioning, you can see this is the metadata query, 13 seconds, so we will be ignoring it. The first query is reading the data. It is taking 5.7 minutes. It is taking more time from the previous one because the data files are now partitioned into different groups like years and months, and there are different directories and subdirectories in the main folder, right? So it will take time for Spark to note all the partitions and all the directories within our dataset. So that is why it is taking more time. Now if you see the reading the full data, it was taking 1.5 minute. Now it is taking 1.4 minute. So it is slight improvement, so we should not be bothered about it. So maybe little improvement. But let's see the third query, that is the filtered one. Previously it was taking 59 seconds, now it is taking 5 seconds. So it is much faster, much faster, and that is happening because of the partition of the data. So let's go ahead and let's see. I will open this in new tabs, this one and this one. So this is the full data read. So same full data, 320 million records we are reading from the storage layer, and we are dealing here with same amount of files. Let's see, it is size of file read is 12.6 GB, approximately similar. The size of file read is little different because we have divided the data based on years and months. So for each year and each month, Spark will create one or more Parquet files, and because of that headers and footers will be there for each file. So maybe that is why the data file size is little bigger, but that is okay. Let's see how many records it is reading. It should read same 320 million records here as previous. And let's see the filtered one. So here you can see it is reading only 16 million records. Okay, so it is going ahead and reading only data that belongs to year 2021 and month in 10, 11 and 12. So that is why the records read from the storage layer to Spark memory is much less. So it is 16 million compared to 320 million here. That is why the time taken is much less. You can see here rows output. Previously it was 320 million, now it is 16 million. And you can see size of files read is also from 12 GB, it is now 650 MB. So it is reading much less data from the storage layer. So let's check the number of files read. Number of files read in the optimized version is 429 files, whereas previously it was reading, let's check how many files it was reading. Number of files read, it was reading 8580 files. So from 8580 files it is reading now just 429 files. So that is why the magic is happening. So Spark is smart enough to understand that my data is partitioned based on this year and month, and I need to look at only this year value of 2021 and month value of 10, 11 and 12. So let's validate that in the physical plan as well. And let's go to the details tab. Here you can see scan Parquet. Now this partition filters, you can see it is filtering based on year 2021 and month 10, 11 and 12 during the reading of the data itself. So that is why it is reading much less amount of data. So Spark is smart enough to push these filters down to the storage layer if the storage layer is designed or segregated based on these filters or based on these columns. So this is called predicate pushdown, and you can see here the partition filters are pushed down to the storage layer here. So we have validated this. Now let's go to the presentation. Compare both query plans. So we have compared both before and after optimization query plans. Check size of the files read in the scan. So we have checked that while reading from unpartitioned data, it was reading 320 million records, but from partitioned data, it is reading only 16 million records. So the number of records are very less, and the number of files are also very small. So previously it was reading 8,500 files, but now it is reading 429 files. Notice the presence and absence of filter in whole stage code gen. Yes, so one thing we need to check here, that let's go here. This is the before notebook. Here you can see scan parquet, then inside this whole stage code gen we have a filter. Okay, but in the optimized version you can see scan parquet, but in this whole stage code gen we don't have any filter. So the filter is pushed down to this scanning step at the very storage layer. So that is why there is no filter in the whole stage code gen. So whenever you are seeing that there is a filter in whole stage code gen step and it is filtering out significant amount of records, so you might consider it as a optimization capability or improvement scope. If the data can be partitioned based on the filters, then we can minimize the number of records read, and that can drastically improve the query results. Check the filters in the physical plan. So we have already checked that those filters are pushed to this very storage layer right here, partition filters. So we validated it. So what is the conclusion here? Conclusion is Spark can push the filters to the storage layer as long as storage system has required support to apply the filters. So if the storage system is partitioned based on the filtered columns, then Spark can push down those filters to the storage layer, and it can read only those records which we are mentioning in the filter condition. And nowadays most of the cloud storage and SQL database as well comes with the capability of this partitioned dataset concept. So if the storage layer is partitioned in a thoughtful manner based on our query patterns we are using in our application, then the query response time can be improved by this technique called partitioning of data, and eliminating the unnecessary rows and reading only the targeted rows that we are interested in. So that's all for this lecture. So see you in the next one. Thank you. Welcome back. So in this lesson you will be learning a problem called directory scan issue. So let's say in your company there is an application team and they came up with a problem statement. So here is the problem statement. They are saying that they have a partitioned data and they are reading very small amount of data using filters on the partitioned columns. So they are applying the filters on the partitioned columns. However, the query is taking unexpectedly long time. So we know that if our data is partitioned based on certain columns and if we are using filters on those columns, then Spark will push the filters down to the storage layer to minimize the data read, right? In the last lesson we have learned that. So it was expected that the query will be taking much less time because the data is partitioned on the columns that we are filtering on, but it is taking unexpectedly long time, and that is their problem statement. Why it is taking so long time to reach such small amount of data based on partitioned column filters? So this is a genuine problem, right? So we know that it should not take more time because my data is partitioned, so they are concerned about it and they want to know why it is taking so long time. So what do we benchmark here? So we will run a filter query that they are using and we'll measure the response time and dig deep how and why it is taking so long time. What is the cluster size that we are going to use in this experiment or benchmark? We will be using single node cluster with 4 core and 14 GB of memory. What is the data volume that we are dealing with here? It is approximately 12 GB of Parquet dataset. Now let's go ahead to Databricks Spark UI to understand the notebook. So I have already spinned up the cluster and started running the notebook, so it is still running. So in this notebook, what we are doing, we are just importing the different data types, and we are providing the schema of our file, and then here we are just reading the Parquet file from this storage location based on the schema that is provided above, and then we are using a filter based on year, month, day and hour, and this dataset is partitioned based on these 4 columns, that is year, month, day and hour. So let's wait and see how much time it is taking to process this job. Okay, so finally the job has finished. So you can see in this step where this spark.read operation is happening, it has taken 24 minutes, and that is quite a significant amount of time for 12 GB dataset, right? And for the filter query, actually it took 5 seconds. So this seems reasonable, but this 24-minute is a really long time to read 12 GB of data. So let's go to the Spark UI to dig deeper. So let's go to SQL and data frame tab. You can see filter and write data, it has taken 4 seconds. That is reasonable, but we don't see this 24-minute anywhere in the SQL and data frame tab, right? So everything looks fine here. So the filter is taking 4 seconds, which is normal, but our actual job is taking way more than that. It is taking 3 seconds, 4 seconds, 24 minutes and 5 seconds, maybe 25 minutes something. So why does this step is taking so long time? Actually in this step we are just doing a spark.read, right? So in this step basically Spark instantiates the data frame. It will not directly go and read the data, it will just instantiate the data frame, and to instantiate the data frame Spark just need 2 information. First of all, what is the schema of the file, and the schema of the file we have already provided in the above, so Spark doesn't need to infer the schema. So schema inference override is also ruled out. So the second information that Spark needs is what is the directory location. So we have provided a directory location here, right? Let's go to the directory location and let's check. Here it is, sales data Parquet, partitioned by year, month, day and hour. So you can see it has partitioned by year on the first level, in the second level it is partitioned by month, on the third level it is partitioned by day, and on the fourth level it is partitioned by hour. So this is a pretty complex and pretty huge directory structure, right? So first the data is partitioned by year, then month, then every month if we have multiple days, and then in every day we have multiple hours, and Spark has to go through all these directories one by one to register what files it needs to read for this data frame initiation operation. So that is why it is taking so long time, because Spark is going inside each directory and subdirectory one by one and going through the files and registering the files that it needs to read so much files from these directories and subdirectories, and this directory structure is quite huge because we have partitioned the data based on multiple columns in a hierarchical fashion, right? So that is why it is taking so long for Spark to even just instantiate the data frame. So this is the directory scan problem. When we create a directory which has multiple subdirectories inside it, Spark requires extra effort to go through each and every subdirectory one by one and register the files inside it. So that is why it is taking 24 minutes, which is pretty long time to read just 12 GB of data. So let's go to our presentation once. So investigation, notice the query execution time. So we have noticed that the actual query execution time is pretty less, but instantiating the data frame is taking way longer than it should have been, right? All queries are running fast, but total time of the job is taking longer. So we have noticed this as well. So what is the conclusion? Partitioning data based on too many columns is not a good approach. So it is not a good design to partition your data based on multiple columns. Maybe one or two columns is okay, but more than that, we'll put an override to Spark to scan the directories, right? Partition should be done based on low cardinality fields. So cardinality means what are the different values a particular column has. So if we want to partition a dataset, make sure that it doesn't have too many unique values. So Spark will not create too many directories for partition by operation, right? For high cardinality fields, Z ordering is a better approach. So we'll learn about this Z order indexing in our following lectures. Although we can partially avoid directory scan issue using the following approach. We first have to create an external table for partition dataset, and we execute MSCK repair on the partition table. So it will partially avoid the directory scan issue, but it is not a foolproof solution. So the better approach is for high cardinality fields, or if we want to partition the dataset or segregate the dataset based on multiple column values, then we may use partitioning and Z order indexing together, or we can use partitioning and bucketing together to optimize our results. Okay. So that is the lesson for this lecture. So thank you and see you in the next one. Welcome back. So in this lesson we'll understand a problem called small files problem. So let's understand the scenario. Suppose in your company there is an application team and they have come up to you with this problem. They're saying that they are reading a full dataset and the read operation is taking long time. So they are reading a full dataset from a directory and they are saying that it is taking longer than usual time. So what is the problem? So they have few questions. Let's go one by one. What is the reason for long time to read data? So as they mentioned, it is taking long time, but what is the reason why it is taking so long time to read? They doubt that they have lot of small files. However, how do they detect this problem? So they already kind of understand that there are a lot of small files in the directory, but they are not sure how to detect this problem, or how to pinpoint, or how to be sure about the problem that it is causing for this lot of small data files. We can run optimize command, but what is the recommended file size for optimization? So they know that they can run optimize command to split the file sizes in an optimized manner, but what is the recommended file size for an optimized read operation? So they want to know that. So let's go ahead and let's see what we want to benchmark here. So we will be executing data frame read operation and investigate if the delay is caused by small file problems. As the team has mentioned that they are kind of suspecting that the read operation is taking long time because of small files, so we will be investigating that. We will be reading couple of other sets of files. So the first set is the same number of records, but it is broken into around 800 MB data files, and the second set is benchmark read operation with around 100 to 120 MB data files. So in all these three data sets, the number of records will be same, but the file sizes will be different. The first case will be small files that is provided by the team. The second set will be benchmarking with around 800 MB each file size, and the third will be with file size around 100 to 120 MB files, and we'll check which file size give us the optimized read operation. So what is the cluster size we will be using for this benchmark? We will be using the same single node standard D4 DSV5 cluster that comes with 4 cores and 14 GB of memory. What is the data volume for this? data volume will be 12 GB per K dataset. So let's go to the Databricks UI to understand the code. So I have already started the cluster and started running the notebook. So by the time it finishes, let's go through the notebook one by one. So here you can see we have 3 cells. In the first cell we are reading the small files, small tiny files that they have provided, the application team has provided us. And the second set is we are reading large files, that is each file around 800 MB size. Okay. And the third set is medium size files, that is 100 to 120 MB of each file size. Just to reiterate that all these 3 datasets contain the same number of records and columns, so the data in these 3 sets of files are same. It is only that the files are splitted in different file sizes. So first one is small, second one is large, third one is medium. We'll check and we'll investigate which file size reads the data the fastest. So let the notebook finish, then we'll dig deeper into the Spark UI. Okay, the notebook has been finished, so let's go to the Spark UI and let's understand what is happening. We'll go to the SQL data frame tab. So here are my 3 queries: read tiny files, read large files, read medium files. The tiny files took 16 minutes to read, the large files took 2.4 minutes to read, and the medium sized files took 2.3 minutes to read. Okay, and let's go and let's open these in separate tabs one by one. So this is a small file ones, tiny file ones. So you can see it has read 320 million records. Now let's open the scan per K. Here you can see number of files read is 40,000. So there are lots of files, but that's okay. They might be using a huge dataset, that's why the number of files are huge, so that's okay. So let's go ahead and check some other things. You can see size of files read, that is 13.8 GB. This is the size of file that is read from the storage layer. Okay, and you can see input read data size total, it is around 23.4 GB. So we can see here the storage, in storage the data files are 13.8 GB, but when Spark is reading these files, the volume of these files are shooting up to 23.4 GB. That's a lot of extra overhead, right? So almost 10 GB of extra read Spark is doing, and this is how Spark reads file. So whenever it is reading file, it will append some overhead or extra cost for each file, and that is why this shooting up is happening. So from 13.8 GB it is shooting up to 23.4 GB. So Spark is doing lots of extra work to read all the small files and to gather all the records. So this is an indication that we have a small file problem. Okay, now let's see one more thing, size of largest file read. So what is the largest file that we have read from the storage layer? It is 364 KB, and size of smallest file read, it is 357 KB. So each file is very tiny, so it is in few KBs. So that is why the number of files are so huge, and that is why Spark is adding so much extra overhead to read each file, to open each file, to read each file, and to register the data into memory. So it is a clear indication that this query is suffering from this small file problem. Okay. So this is the large file one. Let's open the scan per K and let's go to size of file rate, it is 11.9 GB, so around 12 GB. Rows output is same 320 million records, and you can see size of largest file is 850 MB. Size of smallest file is 770 MB. So the file size are around 800 MB approximate average size. So we have considered bigger files in this case. Let's see what is the input read data size here. So this was the size of file read, 11.9 GB. So this is the size of the files in the storage layer. So input read data size total, so it tells us how much Spark is reading the data from the storage layer, including the metadata and the overheads, so it is reading 11.9 GB. so here also size of file read is 11.9 GB, and here also 11.9 GB, so it is pretty much closer. So the overhead that Spark is applying to read the files is not much in this case. So we have checked that these two values are close. So ideally these two values should be close, and if one of these values are much more greater than the other one, then we can conclude that it is a small file problem, as we have checked for the tiny files, right? In this case it was 23.8 GB, 23.6 GB, and here it was 13.8 GB, I think 13.8 GB, so it is quite a shoot up. Now let's check the third case, that is medium sized files. So it also has read 320 million records. Now let's see the scan parquet. In the scan parquet, let's check the size of file read is 11.9 GB, and input read data size total, that is also 11.9 GB. So Spark is not adding much overhead to read these set of files. Now let's see what is the largest size of the file. Largest size of the file is around 101 MB, and smallest size is also around 101 MB. So around 101 MB size file it has so read, and the overhead is not much. Let's go to the stages. So this is the tiny files one. It read 23.4 GB of data, and let's see the large file ones, and let's see the medium file ones. So this is the large file ones. The time taken across all tasks is 9.6 minutes. It has triggered 98 tasks, and time taken for all the tasks is 9.6 minutes. Let's say this for the medium size files. It has triggered 120 tasks, and the time taken for all the tasks to complete is 9.1 minutes. So we have concluded that the medium size files, that is file size of around 100 to 120 MB or 128 MB, is best suitable for reading. So it is most optimized file size for read operation. Okay, so let's go to our presentation. Investigation. Check the SQL plan for the following. Number of rows. So we have checked that in 3 cases the number of rows are same. Size of file read. So size of file read is little bit more for the tiny files, because in each small Parquet files there is header and footer information available. So the file sizes are little bit more compared to the other two, but the number of records in all the 3 cases are same. So size of file read is little bit more for the tiny files, but it is quite same for the medium and large files. Input read data size. So we have seen that the input read data size for the tiny files is much greater than size of files that is present in the storage layer, right? So that is a clear indication of the small file overhead. But in the other 2 cases, the input read data size and the storage layer size of files are almost similar. So it indicates that in the other 2 queries it is not suffering from small file problems. get the same details from the stage. So we have checked the stage details and we have noticed that the time and effort that is consumed by Spark to read the small files is the greatest, whether the other two cases it is taking very less time. So there are some additional indicators from where we can check if it is really suffering from small file problems. So let's see once again. So this is the tiny file once. It has the number of files read is 40,000, but for the same data here, that is large file once, the number of files read is 15. So each file around 800 MB we mentioned, and for the medium size files the number of files read is let's check, it is 120. So from here also we can understand that the first case we have 40,000 files and it is suffering from small file problems because 13.8 GB of data into 40,000 files, so the file sizes are very small as we have validated from this largest and smallest file read, right? So number of files read, we have checked that size of the largest and smallest file read, so we have validated that as well. So what is the conclusion here? Conclusion is you can detect small file problems from the scan details. So in scan Parquet or scan CSV or whatever dataset you are scanning, if it is taking much longer time to scan the files, and if the gap between the size of the files and the size that is Spark considering including the overhead is wide enough, then we can understand it is suffering from small file problem. And the next conclusion we made that moderate or medium sized files performs the best. So around 100 to 120 MB files generally performs the best. That's all for this lesson. See you in the next one. Welcome everyone. In this lecture we'll understand a problem that is known as haystack query problem. So haystack query is basically finding a needle in a haystack. So if we have, let's say, 100 or 200 GBs of data and you want to find only 5 or 10 records out of it based on certain filter values, so it is like finding a needle in a haystack, right? So how we can optimize this sort of filtering? So let's check and let's see with an scenario. So let's say you have a application team and they are facing an issue regarding this, so they have come up to you with this problem statement. We are working out the best strategy for creating a partition table. So they have a large data set and they are working out by looking at their filters what kind of query patterns they will be using on top of this data set to understand what should be the partitioned column. Okay. Our analysis is to partition the table into year, month, day and hour fields. So they want to partition their data set based on year, month, day and hour fields. However, they know that it might be an over partition and this can cause a direct scan problem, as we have learned earlier, right? So creating partition based on too many columns can cause a direct scan issue. So they know that, and that is why they are asking us for help. So let's get to their questions. How will day and hour queries perform without day and hour partitions? So they know that if they will create partitions based on year and month, so it is okay and it will not cause much direct scan problem. But in that case, how will the day and hour queries will perform without day and hour partitions? So they are worried about the query performance. How we can optimize day and hour filters without over partitioning? So without over partitioning, how they can filter faster if they want to use this day and hour filters in their filter conditions. So we will check how we can optimize that. So what do we want to benchmark? We will execute filter operation on two different sets of same data. So we have two versions of same data. What are the two versions? First one is only partition data set based on year and month. Okay, so the first set is the full data and it is partitioned based on year and month. So the second version of the data is partitioned based on year month, plus it is Z ordered indexed based on day and hour. So we will run our query on both these datasets and we will compare the results. What is the cluster size that we are using here? We will be using single node standard D4 DSV5 cluster that comes with 4 core and 14 GB of memory. What is the data volume that we will be using here? We will be using 60 GB of delta dataset for this benchmarking. Let's go to Databricks UI and let's do this benchmarking. So I have already spinned up the cluster and let's run this notebook. So in this cell we are reading a delta dataset from this directory and it is partitioned based on year and month only. Okay, and in this cell we are filtering the above dataset based on year, month, day and hour. So we will filter this dataset based on these 4 columns and we will see how long the query takes. Okay, the notebook has finished running, so it has taken 41 seconds. So let's go to the Spark UI. By that time, let's run our modified or optimized version of this query. So here also we are using the same delta dataset from this directory. The only difference is that it is partitioned by year, month and Z ordered by day and hour as well. And on top of this Z ordered cells, we are applying the filter based on year, month, day and hour. So same filter, and let's see how long it takes to filter this data in this optimized version. Okay. So the notebook has finished. Let's go to the Spark cluster to check out the details. Let's go to Spark SQL data frame tab. You can see here, this is the query sales data. It has taken 41 seconds. So this is the guy that runs on top of only year and month partitioning. And this is the query z.sales. This has taken 6 seconds. So this is quite an improvement based on the previous version, right? So this dataset is partitioned by year and month as well as z ordered by day and hour. So we can see much improvement in the second case. So from 41 seconds to 6 seconds. So it has improved quite a lot. So let's go ahead and let's dig deeper into each of these query plans. So in this case, we can see we are reading 31 million records from the scan parquet, and then this 31 million records is going into the filter based on our condition, and it is filtering out rest of the data and only selecting 43,000 something records. So it is filtering out quite a large number of records. So let's see the details of this. You can see scan parquet step here, and in the scan parquet step we can see partitioned filters, is not null year, is not null month, year equal to 2020 and month equal to 4. So it is pushing down the partition column filters down to the storage layer to minimize the data read size, right? But in the pushed filter you can see not null transaction date and not null transaction time. So the pushed filter is only not null. Okay, now let's go ahead and let's check the second guy, that is Z ordered sales. In this case we are reading only 15 million records. In the previous case we are reading 31 million records, and in this case we are reading 15 million records. So that is half of the data. So it has improved quite a bit. And here also we are using the filter to filter our targeted records, that is 43,000. So in the previous case also it was 43,000. Okay. Now let's see in the second guy, that is Z ordered index data. Let's see the details of the physical plan. scan parquet step 1. So let's go to step 1 scan parquet and let's see the partition filters. So in this case we have is not null year, is not null month, and here also year 2020 and month 4. So Spark has successfully pushed the filter columns down to storage layer because our dataset is partitioned based on these two columns, right? So this is okay, but additionally in this case we have pushed filters. You can see not null day, is not null hour, equal to day 3, equal to hour 7. So Spark has additionally put these two filters down to storage layer because our dataset is z-ordered indexed, and Spark knows that our dataset is z-ordered indexed based on these two columns which are using in the filter condition. So that is why Spark is pushing these filters as well to the storage layer, and that minimizes the record read size. Okay, our storage layer is configured to handle these kind of filters because we have used z-ordered indexing. Now one more thing we need to check here, that is the scan parquet step. So let's see how many files we have read here. Number of files read. So in the only partitioned case we are reading 844 files because it is partitioned based on year and month, and within a month there might be multiple files. So it seems that it has 844 files for this year month combination, and Spark is reading all the 844 files to filter out the targeted data. And you can see here the size of file read, it is 748 MB. So this much data we are reading for this filter condition. And for the z-ordered case, so you can see number of files read is 1. That is significantly lower than the previous case, right, where we are reading 844 files, and here in this case we are reading only 1 file. So that is a significant improvement. And let's see the size of the data we are reading. Size of file read, that is 398 MB. So approximately 400 MB data we are reading here, and that is why the job is taking so much less time to filter the records. And you can see here size of largest file read is 398 MB. So in the only year month partitioning case, Spark is able to prune or exclude the directories that is not based on this filter, right, that does not have data belonging to year 2020 and month 4. But after excluding all those records as well, Spark is reading 844 files, right? You can see number of files is 844. So partitioning helps Spark to exclude all the directories that does not have our target data. But in case of partitioning plus z-ordering, after excluding all the directives based on the partitions, z-ordered indexing is also helping Spark to exclude the files based on the filter condition. So z-ordered index helps Sparks to pinpoint the files that may have values corresponding to our filter condition. So here in this case, for day 3 and hour 7, z-ordered indexed has helped Spark to identify only one file, and that is why Spark is reading only one file. And this file size is quite large, actually around 400 MB. So there is no other way to reduce this because Spark have to read the full file to filter the data. So this is one of the reasons why we should not get too large files. So if the file size is around 120 MB, then Spark would have read around 120 MB of data for this one file, right? So that would have taken even less time for this query to run. So medium size files around 100 to 128 MB works best. However, in this one file that Spark has identified that our targeted data might be present, it may have records other than the filter conditions as well. So our filter condition is based on day 3 and hour 7, and this one file may have let's say day 4 hour 3 or day 5 hour 2, this kind of records as well. And that is why this filter condition is also required, because z order index is not a foolproof filter, so it helps Spark to exclude the files that is certain not to have our target data. So it is not guaranteeing that the file that it is identifying will only have our target data. So there might be other values as well in the identified file or files. So that is why this filter condition is also required, and that is why it is filtering out quite a large number of records in this case, right? So from 15 million to 43,000. But we know that this filter is required because if we create too much partitions, our job will suffer from directory scan issue. So this filter is also required. So we cannot totally eliminate it, but we have reduced the data read size from the storage layer, and that has significantly improved the query performance. We have checked the SQL plan and compare the following things. How many rows we are reading? So we have checked that for the first case we are reading twice as many rows as from the second case. So in the z ordered case we are reading much less amount of data, right? Why filters in the whole stage code gen? So we have also learned that this filter in the whole stage code gen is required because z ordered indexing is not a foolproof filter. It helps Spark to exclude the unnecessary files, but it cannot guarantee that only targeted data will be present in the identified files. So there might be other data as well. So in order to exclude those records, this filter is required in the whole stage code gen. Number of files read. We have checked that for the first case the number of files read is much larger than the second case. In the z ordered case, Spark has identified that this only one file is required to read the targeted data. And physical plan for push filters. So for push filters we have seen that Spark is actually pushing the filters to the storage layer based on the indexed column, right? So day and hour of filters are also pushed down to the storage layer, then that is why file skipping is happening. So what is the conclusion from this lecture? Partitions allow skipping the entire directory. So it is called partition pruning. So we will prune or exclude the partitions that will not have the intended records. So partition allows skipping the entire directory, whereas z ordered allows skipping data files. So in a particular directory there might be 100 or 200 files, but z order will allow Spark to identify that our targeted values will be present only in these 5 files or 10 files like that, and Spark will read only those files in order to minimize the data read size. Z ordered index allows predicate push down to storage layer. So we have validated that from the pushed filters, right? So Z ordered index is actually allowing predicate push down to storage layer. Z order is very efficient for needle in a haystack query. So let's say we want to filter 5 or 10 rows from a 100 GB dataset, or let's say we want to filter a dataset based on primary key. So in those cases z order index is very efficient because it will pinpoint the file which will be having that particular record or set of records. Partitioning is good for low cardinality fields, whereas z order is great for high cardinality fields. We can mix partition and z order indexing for best results. So the best approach is we should use partitioning as well as z order indexing to optimize our query performance. So that's all for this lecture. Thank you. See you in the next one.